Greetings everyone, welcome back to General Chemistry. I apparently underestimated all of the unexpected twists and turns that I was going to encounter last week. This video I was expecting to release over a week ago, and you know, between a sore throat and a bunch of unexpected work, it ended up getting delayed. At this rate, I probably won't get much of this series done by August. I'll probably have to continue working on it into September, which is not going to be ideal because September is usually when the tutoring requests start piling up and I have even less free time available. But, you know, that's a concern for me. Not something you need to know too much about. Well, I mean, you might be worried about it if you really like this series already. But without further ado, let's just get straight to our next topic, which is gas laws. So, for this video, we're going to talk about gas laws, and our first subtopic is going to be the concept of pressure. The concept of pressure. What is it? So the concept of pressure is defined in physics as the ratio of the force applied to an object divided by the surface area, the area over which that force is being applied. So in physics, pressure is equal to force over area. So for example, if I have, let's say, a 10 kilogram block on top of a surface that has an area of, let's say, I don't know, let's make this 5 square meters. Yeah, let's say this is an area of 5 square meters, and let's say I put a block on top. Let's say I put a block on top of here that has a mass of 10 kilograms. Let's see if I can draw this correctly. I probably should move this beaker out of the way. You can't see it on the screen, but there was a beaker on the edge of the table. Okay, so let's see. Let's say this is a 10 kilogram block. Now, if you know your physics, then you know a 10 kilogram block has a weight of about 98 newtons. So the force that it applies downward is equal to 98 newtons of force. Some people will just round that to 100, which I guess is fine. We're not here to do physics, but I'll just stick with 98 anyway, just so that I don't get, you know, crucified by the physics enthusiasts in the comment section, I mean. And yeah, where was I? Lost my train of thought. So we've got the force, we've got the area, so then the pressure that this block exerts on this yellow tile that I drew would be 98 divided by 5. Pressure would be 98 over 5 equals, let's see, 98 over 5, that's almost 20, it's 19.6. 19.6 newtons per square meter, because I divided newtons over square meters, or 19.6 PA, which stands for Pascal. The standard unit of pressure is the Pascal. P-A-S-C-A-L. But remember that a Pascal is a Newton per square meter. That's going to be important later when we do a certain conversion, and we'll have to bring in another physics concept at that time, but all in due time. So yeah, that's the basic unit of pressure, is the Pascal. In chemistry, we rarely use actual pascals, but we do encounter some of the other units of pressure. So one unit of pressure that's typically used in chemistry is the atmosphere, the ATM for short. It represents exactly 1 times the amount of atmospheric pressure that the atmosphere exerts on the surface of the Earth at sea level. So one atmosphere is equal to a lot of pascals. It's 1.01325 times 10 to the 5 pascals. And I did not leave enough room for this, did I? Pascals. So yeah, that's over 10,000, or no, over 100,000, I should say, pascals. More than 100,000 pascals. Another very similar unit to the atmosphere is the bar. Another unit is the bar, and 1 bar is equal to 1 times 10 to the 5 pascals. This is a perfect conversion. This is an exact conversion. 1 bar is exactly 10,000 pascals. Another unit we encounter has multiple different names. The millimeter of mercury. Well, just 2 different names, really. The millimeters of mercury or the torr, and we'll see why millimeters of mercury are a unit of pressure when it seems more like a unit of length. But yeah, let's see. So I can't convert this directly to pascals, but I do know how to convert it between atmospheres. So 1 atmosphere is equal to 760 torrs, or 760 millimeters of mercury. We'll make sense of the names for this, or of the name for this unit later, or the 2 names rather. And finally, the last one I want to bring up is the PSI, the pound per square inch. So the pound per square inch, hopefully we won't have to deal with that often, because, you know, it's not really a metric unit. It's from the US customary system of units, which is, you know, not exactly my favorite system of units, as I alluded to in a previous part. I think I remember going off on a little rant about Lincoln Chafee and his prospects as a candidate, but I digress. The pound per square inch. So pounds are kind of weird in that they are units of mass, but they're also used as units of weight, and weight is a force. So it follows the same logic of force over area that we used over here for the Newton per square meter, also known as the Pascal. The pound per square inch, kind of similar. It's force over area. So 14.7 PSIs are equivalent to 1 atmosphere worth of pressure. Now, according to some books, it's 14.69. Other sources say 14.70. So I'm just going to be on the safe side and keep only 3 sig figs for the PSI to ATM conversions. But if you have confidence in 14.69 or 14.70, if you have confidence in one of them being more true than the other, you're more than welcome to use those. I'm just going to play it safe and go with 14.7, just round it to 3 sig figs. Okay, so how is pressure measured? How do we measure pressure other than, you know, calculating it, calculating the force and dividing by the area? There is a way to measure pressure, in fact, 2 ways to measure pressure, which I will show you. First method I want to show you is this right here. So that device you see on your screen right now is called the barometer, or barometer if you prefer. And this device was, I guess the appropriate word would be designed or used by Evangelista Torricelli to measure atmospheric pressure. The way it works is the pressure of the air, the weight of the air above your head and above, you know, the entire Earth. Air might be light, but it still has weight. It still exerts a force downward on you, even if you don't feel it. It's only because you're just used to it. But the air pushes down on everything. Everything on the surface of the Earth has a bunch of air pushing down on it. And when the air in the atmosphere pushes down on that gray fluid in the barometer, and that gray fluid just so happens to be mercury, then what happens is the mercury starts going up that big tube in the middle. And the greater the pressure, the greater the atmospheric pressure that's pushing down on the mercury, the further up the mercury goes in that long tube. And basically, the higher it goes in the tube, the greater the pressure. And it just so happened that significant changes in atmospheric pressure only caused the mercury to rise very small amounts because of the high density of mercury, and because of that you could measure significant changes in pressure by just watching the height of the mercury in that middle tube going up or down by just a few millimeters, and that's why the units of millimeters of mercury exist. It's just a direct measurement of how high the mercury goes up or down in that middle column, measured in millimeters. However, millimeters of mercury are also called torrs, and the reason for that, if you haven't figured it out already, is because it's named after the scientist who designed this device. Evangelista Torricelli. I think I'm pronouncing it right. Evangelista Torricelli. I'll write it down here. Evangelista Torricelli. I'm probably spelling it wrong too. Evangelista Torricelli. I think it's 2 C's and 2 L's. Who knows? But yeah, you can spell check me if you want to. I'm not gonna point that out in my list of mistakes caught in a comment because I just want to focus on the chemistry specific mistakes. But you know. So yeah, that's why it's called the torr. So it can be called millimeters mercury or torrs. Millimeters mercury because of how the barometer works. Mercury just goes up or down by a few millimeters. When you go up or down a few dozens of meters on land to notice changes in atmospheric pressure, and the units are also called torrs, named after the scientist who came up with this device. Alright, so that's units of pressure. Let's practice converting between them. I feel like I'm forgetting something. Oh, right, one more thing. There's one other tool that we have for converting between different units of pressure, and that is the manometer or manometer. So let's switch to that real quick. So here's another device that you see on your screen that can be used for measuring pressure. So the way it works is you have gas trapped in a container on one side of the manometer, and on the other side you can either have a closed end or an open end. It doesn't really matter. If it's an open end, you just have to take one more thing into consideration with your calculations, which is the atmospheric pressure pushing down on the open end, but this is a closed end device, so we won't worry about that for now. We'll see an example of both later. But yeah, the idea here is that you notice the liquid, which in this case is again mercury, you notice that the liquid is a little higher on one side than the other, and the reason for that is because of the pressure of the gas. The gas exerts enough pressure on the left side to push the right side up, such that the height difference in the case of the example you see in front of you is 26.4 centimeters. And that 26.4 centimeters, if you consider how much pressure 26.4 centimeters of mercury creates, then that must be equal to the pressure of the gas. So basically, and let me try just drawing this so that I can explain it more clearly. If you have this U-shaped tube, let's say this is a closed end, and let's say this end has the gas. So there's your gas. Let's say there's the height of mercury there. And let's say the height of mercury on this end goes up to here, for example. And let's go ahead and shade that. Basically, the pressures that end up down here at the bottom must be equal. If there's more pressure on the left side than on the right side, then the liquid will continue to be pushed up. And if there's more pressure on the right side than on the left side, then the liquid will continue to be pushed to the left. So the idea is that the pressure on both ends needs to be equal. We already know that the pressure from this section right here, so this bottom section under the dotted line, we know the pressures on both sides must be equal because, well, they're equal amounts of mercury and they exert equal amounts of force because they have equal amounts of weight. This over here creates an equal amount of pressure to this, right? So what I shaded in peach and what I shaded in yellow, those exert equal pressures. One exerts an amount of pressure to the right. Whatever pressure that is, we don't care. We know an equal amount of pressure is being exerted to the left by the yellow part. And so they cancel each other out. We don't need to know how much pressure these two parts are. That just leaves the gas part and this excess mercury on the other end. Those must be equal in pressure then. So since we've already canceled out those two sides, we know that whatever pressure this extra mercury would create, that must balance out with the pressure of the gas. Maybe that was already obvious to some of you, but just wanted to try and clarify it just to be on the safe side. Okay, now we're ready to look at a couple of conversion problems. Let me switch this off and get that ready for later. And let's go ahead and look at some pressure conversion problems. Okay, so it says, for number 4, a typical barometric pressure in Redding, California is about 750 millimeters of mercury. Calculate this pressure in atmospheres and kilopascals. Kilopascals. Let's see. So kilopascals shouldn't be too hard to understand if you already know your scientific notation. Let's just go ahead and do this real quick. Which marker should I use? Let's go for this one. I haven't used it yet. So we've got 750 millimeters of mercury. And we need to convert this to kilopascals. Okay, well, I've got all my conversions right here. So to get to kilopascals, I need to get to pascals, and to get to pascals from millimeters of mercury, first I have to go through atmospheres. So let's go ahead and do that. So 750 millimeters of mercury. I know that 760 millimeters of mercury is equal to 1 atmospheric pressure. Then from atmospheric pressure to pascals, we've got, let's see, 1 atmosphere is equal to, I don't want to take all the digits because I know I'm going to end up with 3 significant figures anyway. Let's just go with 1.013 times 10 to the 5. So 1.013 times 10 to the 5 pascals. And then converting pascals to kilopascals, I can say that 1 kilopascal is equal to 10 to the 3 pascals, or 1,000 pascals if you prefer. But yeah, that's an exact conversion, so 10 to the 3 and 10 to the 5, I can reduce those, leaving us with 10 squared up here. But yeah, the rest is calculator work, and I found my calculator just in time. So we've got 750 times 1 over 760 is 0.987. 0.987. And then multiply that by 1.013 times 10 to the 2. If you reduce the 10 to the 3 and 10 to the 5, that becomes 10 squared. So yeah, multiply 0.987 by 1.013 times 10 to the 2, and that gives me 99.9831, which I guess I will round to 100 point. So I get, at the end of the day, 100 point kilopascals, kPa. And yes, that decimal point is necessary to show that the 2 zeros in the 100 are indeed significant figures. You can also write it as 1.00 times 10 to the 2 kilopascals if you prefer. That would be even better at showing that the zeros are significant. Okay, so that was one conversion problem. Let's do another. Number 5, we already did something like it. Oh, wait. Number 4 said calculate in atmospheres and kilopascals. Okay, well, we did atmospheres anyway, so that part's done. Number 5, pressure in atmospheres and kilopascals. Again, we've already done that, so we'll skip it. Number 6, we've got 740 torr, which is the same as millimeters mercury. Find it in atmospheres, millimeters of mercury, and kilopascals. So that second ask is a trick question. What is 740 torrs in millimeters of mercury? Still 740, because 1 torr is 1 millimeter of mercury. But yeah, number 6 otherwise is pretty much the same. Number 7, Canadian Tire pressure gauges are marked in units of kilopascals. What reading on such a gauge corresponds to 32 psi? Okay, let's do that one because I think that's the first one we've seen that actually mentions the units of psi. So it said that Canadian Tire pressure gauges are marked in units of kilopascals, and they want 32 psi, 32 pounds per square inch, converted to kilopascals. Okay, so of course we want to go to atmospheres first, and then from atmospheres we can go to pascals, and then from pascals to kilopascals. So kind of the same as what we had in that first problem we did. 32 psi, so every 14.7 psi is equal to 1 times the atmospheric pressure at sea level, and then every 1 atmospheric pressure at sea level is equal to 1.013 times 10 to the 5 pascals, and every 1 kilopascal is equal to 1,000 pascals. Let's see, 32 over 14.7 is 2.2 if I round it to 2 sig figs, so 2.2 atmospheres. I forgot to include that over there. 2.2 atmospheres, and then, let's see, I can reduce the 10 to the 3 with 10 to the 5. I guess I can cancel the whole thing, really, and get 10 squared over there. Yeah, should have crossed out the whole thing. And yeah, then pascals are eliminated and you get kilopascals. So 2.2 times 1.013 times 10 to the second gives us 222.86, which I'm going to round to 220. So that's going to be 220 kilopascals. Of course, since it's 2 sig figs, it would be more proper to write it as 2.2 times 10 to the 1 kilopascals. That way it's very clear that it's 2 sig figs and not 3. Alright, so there's that problem, quick and easy. You just need to know the conversion factors. Number 8 says, during the Viking landings on Mars, the atmospheric pressure was determined to be on the average about 6.50 millibars. And they actually gave you a conversion factor between bars and atmospheres. What is that pressure in torrs and kilopascals? Okay, let's go ahead and work with bars. So I guess I'll go with yellow for this one. So they said, let's see, it was 6.50 millibars. 6.50 millibars. Millibars. Okay. 6.50 millibars. So to convert millibars to bars, I can say that 1 millibar is equal to 1/1000th, or 10 to the negative 3 of a bar. Once we've converted to bars, there is a conversion between bars and pascals, but there's also a direct conversion between bars and atmospheres, because since a bar is 10 to the 5 pascals and 1 atmosphere is 1.01325 times 10 to the 5 pascals, that 10 to the 5 pascals can be replaced with bars. So we can also say, and I should add this to the list, 1 ATM is equal to 1.01325 bars. And let's go ahead and use that as a conversion factor rather than the one they gave us in the problem, because I just have to be that guy. 1.013 bars, I'm not going to use all the digits, is equal to 1 atmospheric pressure at sea level. I have to keep emphasizing that it's at sea level because the pressure of the atmosphere depends on your elevation. Atmospheric pressure on a mountaintop is way less than atmospheric pressure at sea level, which is still less than atmospheric pressure below sea level. Where was I? Probably shouldn't have gone off on that tangent. Okay, so we're at atmospheres and we're trying to get what again? It said torrs and kilopascals. So I guess from here we can go in 2 different directions. So let me scribble out this set of parentheses. And so option 1, we can convert to torrs. So 1 atmosphere is equal to 760 torr. And the other option they want us to take is convert it to kilopascals. So let's see here. 1 atmosphere. Oh, how many kilopascals is 1 atmosphere? Well, I can do that. So 1 atmosphere is equal to... Actually, wait. No, I could just go straight from bars to kilopascals. I don't even need this. Scratch this step. I can go straight from bars to kilopascals. 1 bar is 10 to the 5 pascals, which is also 10 squared kilopascals. A bar is 10 to the 5 pascals, a kilopascal is 10 to the 3 pascals, so a bar is just 100 times a kilopascal. So I can go straight from bars to kilopascals. 1 bar equals 100, or 10 squared kilopascals. Okay. Now let's go ahead and calculate using both methods. So we have 6.50 times 10 to the negative 3. I guess if I multiply that by 10 squared, then I get 6.50 times 10 to the negative 1, which is equal to 0.650. So the first one, I don't even need a calculator. 0.650 kilopascals is what we get for that one. Yeah, 2 exact conversions there. Here we have an unexact conversion, so we're going to have to do some rounding at the end of this one. 6.5 times 10 to the negative 3 divided by 1.013. Oh, forgot my division. There we go. So that gives us 0.00642. So 0.00642 ATM. And then multiply that by 760. So 0.00642 times 760. That would round to 4.88. 4.88 torrs. Very, very small pressure compared to the atmospheric pressure at sea level. But yeah, if we measured it in pascals, I think pascals would be fairly appropriate units. If I converted this to pascals, it would be 650 pascals. While pascals may be the official unit for pressure, they're not always the most appropriate unit. I mean, imagine giving somebody their blood pressure in pascals. Fun fact, blood pressure is measured in millimeters of mercury, and I actually have a blood pressure monitor. Let me bring that to the screen real quick. Let me try and keep all the wiring and circuitry out of the way, but yeah, this is a blood pressure monitor. I guess I'd have to plug it in to show it, but oh goodness, I don't think this cord is going to reach. And of course there is no battery in this thing, so I can't really power it up for you guys, but this blood pressure monitor, if you're willing to believe me, when you turn it on, it does actually show you that the units of measurement are millimeters of mercury, or torrs. And yeah, a healthy blood pressure would be about 120 millimeters of mercury for your systolic pressure and 80 millimeters mercury for your diastolic pressure. Anything above that is considered, you know, at risk of heart disease. And yeah, there was a time when my blood pressure was kind of higher than usual. I've brought it down to healthy levels now, so no need to get scared, but that's basically the reason why I bought this thing, to keep track of whether or not my dietary changes were actually having any effect. Anyway, let me go back and put this away. And imagine if we gave people their blood pressure in pascals rather than millimeters of mercury. Let me go ahead and do that calculation real quick, just for fun. So let's see. A systolic pressure of 120 millimeters mercury is considered healthy. Let's convert that to pascals. So I know that every 760 millimeters of mercury is 1 atmospheric pressure, which is also 1.013 times 10 to the 5 pascals. So I'm kind of skipping steps there, but you want to get to the level where you can do this kind of smoothly. If you can see what I did there, just jumping straight from skipping atmospheres entirely and jumping straight to pascals, if you can master that skill, that'll be very helpful. But anyway, if I go ahead and convert this, so 120 times 1.013 times 10 to the 5 over 760. So that's almost 16,000. So yeah, imagine a doctor telling you your systolic blood pressure is 16,000 pascals. Congratulations, you're healthy. I imagine people who didn't know their units would have a heart attack right then and there. But I digress. Do I have other pressure conversion problems to look at? Oh, yeah, we have some manometer problems to look at, I think. Let me see. First, let me read through these problems real quick and see if any of them are interesting. Pressure of atmosphere on the surface of Venus is about 88.8 atmospheres. Compare that pressure in pounds per square inch to the normal pressure on Earth at sea level in pounds per square inch. I mean, I think that one is a wild goose chase, because if you convert them both to pounds per square inch, the ratio is still going to be 88.8 to 1. I hope you can see that. If you can't see that immediately, then it's worth it to sit down and think about it rather than have me explain it to you. If pressure at sea level on Earth is 1 atm and pressure on the surface of Venus is 88.8 atmospheres, what does that tell you about the ratio of the PSI pressures on Earth versus Venus? Number 10, a medical laboratory catalog describes the pressure in a cylinder of a gas as 14.82 megapascals. Capital M stands for mega, if you remember your scientific conversions. 1 mega of anything is 1 million of that unit. What is the pressure of this gas in atmospheres and torrs? So nothing too fancy there. You just need to convert megapascals to pascals first, and then the rest is history. We've already seen how to do stuff like this, so let's read the next one. Number 11 says, consider the scenario and answer the following questions. On a mid-August day in the northeastern United States, the following information appeared in the local newspaper. Atmospheric pressure at sea level, 29.97 inches mercury, 1013.9 millibars. Part A, what was the pressure in kilopascals? Part B, the pressure near the seacoast in the northeastern United States is usually reported near 30 inches mercury. During a hurricane, the pressure may fall to near 28 inches mercury. Calculate the drop in pressure in torrs. So that's another thing that this question actually helps bring up, is the fact that atmospheric pressure at sea level is not constant. It depends on weather conditions. but I guess you could say that the value that we're using is like the average or standard pressure at sea level. I'm not really sure under what conditions they consider it to actually count, but just know that if you go to a place that's at sea level, the pressure there is not necessarily 1.013 times 10 to the 5 pascals every single minute of every single day. But yeah, carrying on. So with number 11, the new wrinkle is that it's using inches of mercury rather than millimeters, but everything else seems like stuff we've already seen. So let's just take a look at converting the inches of mercury to millimeters of mercury, and you can carry out the rest of the problem on your own. Okay, converting between inches and millimeters. So if you remember how to convert between inches and centimeters, you should actually be fine. Let's see. So we've got 29.97 inches of mercury. So I can convert inches to centimeters because I know that every 1 inch, or in this case 1 inch mercury, is equal to 2.54 centimeters, and this is an exact conversion, so we don't lose any sig figs or decimal places. Then from centimeters to millimeters, 1 centimeter is 1/100th, 1 millimeter is 1/1000th of a meter. So I guess just to be super formal about it, you can say 1 centimeter is equal to 10 to the negative 2 meters, and then let's see, 1 millimeter is equal to 10 to the negative 3 meters. So that's if you wanted to write out every single step and couldn't immediately see that a millimeter is just 1/10 of a centimeter. I think everybody knows that, but it's good to show how to do it the long and hard way, because sometimes when you're confused, doing it the long and hard way is easier. Oh, and I forgot to write mercury for each of these. But yeah, let's go ahead and work this out. So 29.97 times 2.54. So we had 4 sig figs, infinite sig figs, infinite sig figs, so rounding to 4 sig figs would be 76.12. 76.12 centimeters of mercury. And of course, if you go through those 2 steps, then you're going to end up with 761.2 millimeters of mercury, and then from there you can convert that to atmospheric pressure, and from atmospheric pressure you can convert it to pretty much everything else. And yeah, so that's the only part of that problem that I'll do for you. You can handle the rest of it on your own. Number 12 says, why is it necessary to use a non-volatile liquid in a barometer or manometer? So that's more of a conceptual question. And the reason you want to use a non-volatile liquid, well, first we need to talk about what non-volatile means. So a volatile liquid is one that evaporates easily. The problem with liquids that evaporate easily is that if they evaporate, then they form a gas, and if they form a gas, that gas can create pressure in the tubes for the barometer or manometer, and that pressure might affect your readings. So this is kind of like precipitation in a way, where when we were talking about precipitation, I think I mentioned how even though we were classifying different solids as being soluble or insoluble, the truth is that everything has at least some solubility, even if it's very small. Same thing with volatility. So there isn't really such thing as a purely non-volatile liquid. There are liquids with high volatility and liquids with low volatility. But yeah, mercury, depending on which source you read, some people describe mercury as a volatile liquid, some people describe it as non-volatile, and I had to do some research to confirm the truth. And basically, all the people that describe mercury as volatile are people who work with mercury in, you know, high temperature environments. And at high temperatures, yes, mercury is very volatile, but at normal room temperatures, mercury is not that volatile. So mercury is a very suitable liquid to use in pressure measuring devices. But let's take a look at the problem a little bit, and we'll get into this more when we talk about vapor pressure pretty soon. Actually, maybe we should talk about vapor pressure now. Nah, we'll leave it for later. But let's say you've got your barometer. So you've got your tube, and it's dipped inside of some mercury. And of course, that mercury can start moving up in the tube up to some sort of level, and let's say some of that mercury evaporates. Let's say some of that mercury evaporates inside the tube, so you have some particles of mercury gas up in here. Well, those particles of mercury gas are going to create pressure and push back down on the mercury, so the mercury won't go as high up as it normally would. It's basically turned your barometer or barometer into a manometer, right? It's basically turned into one of these devices where there's a gas pushing the mercury back down to the other side, except here you don't have a left side and a right side. You just have, you know, a top and a bottom. And yeah, so the gas pushes the mercury down a little, so the reading ends up being an underestimate of the actual atmospheric pressure on the outside. But yeah, that's how a volatile liquid can mess with the calculations. And again, everything is volatile. Every liquid is volatile to some degree, but when we say non-volatile, we mean really, really low volatility that won't, you know, mess with our measurements too much. Okay, so that takes care of that conceptual question. Now let's take a look at some of those manometer questions. Okay, number 13 says the pressure of a sample of gas is measured at sea level with a closed-end manometer. The liquid in the manometer is mercury. Determine the pressure of the gas in torrs, pascals, and bars. If the liquid is not mercury, you will learn in either a general physics course, or if you're in high school, maybe AP Physics 2 or Honors Physics, you'll learn how to do the calculation if the liquid is not mercury. For chemistry, the liquid will always be mercury, so you don't have to worry about it, unless your chemistry teacher is also a physics teacher, in which case, God help you. But yeah, let's take a look at this. So that was the original image that I showed you in the beginning. So it's 26.4 centimeters of excess mercury, and that excess mercury must balance out with the pressure of the gas. So once you convert the 26.4 centimeters mercury to millimeters of mercury and then to atmospheres, then you can just go from atmospheres to torrs, pascals, and bars. So it shouldn't be too hard to do. This is with a closed-end manometer. So let's go ahead and do that. Let's draw our... Well, do I need to draw it really? No, I can just do the calculations. So it was 26.4 centimeters of mercury. That easily converts to 264 millimeters of mercury. 1 centimeter is equal to 10 millimeters. And I guess I should write mercury there. And then from there I can, well, I guess I have it in torrs now, and to get it in pascals and bars, I would go to atmospheres first. So every 760 millimeters of mercury would be 1 atmosphere, or 1.013 bars. So let's go ahead and calculate. We've got 264 millimeters of mercury, which is the same as 264 torricellis. And then 264 over 760 times 1.013. 264 times 1.013 divided by 760. That gives me 0.352. So that's 0.352 bars. And if you multiply that by 10 to the 5, 1 bar is 10 to the 5 pascals, so 0.352 times 10 to the 5 if I convert it from bars to pascals. And there we go. So that answers parts A, B, and C. So that's for the closed-end manometer. Let's take a look at another one. Let's pull up manometer number 2. So it says again pretty much the same thing. Oh, and they gave us a conversion factor for convenience. 29.92 inches of mercury is equal to 1 atmospheric pressure at sea level. Let's see. So they wanted in torrs, pascals, and bars again, but this time one of the major differences is that there is an open end. So how does that change things up? Well, the way that changes things up is that the atmospheric pressure now also is applied on top of the open end. So you've got two excess pressures to take into account. Let me go ahead and actually draw this out on a second page, or not a second page, but you know, a new page. Let's go ahead and draw this out. So we've got the gas, and this time the gas is actually pushed back, so the mercury is higher on the gas side of the manometer. That can happen sometimes, especially if the gas has a low pressure and can't push back. I mean, how could it push back when you've got not just some mercury, but also some atmospheric pressure pushing down on the other end? Okay. And I guess I should mark the mercury level there, and let's do a dotted line. And yeah, so this time the excess mercury is on this side, and it's 6 inches worth, 6.00 inches worth. Okay. So over here the pressure here should be equal to atmospheric pressure. So everything below the dotted line I don't need to worry about. All pressures above the dotted line need to be equal to each other. So down here we've got the atmospheric pressure, so I guess you could say pressure of the gas plus pressure of the excess mercury, which is the 6 inches, has to be equal to the pressure on the opposite side. The pressure at this point has to equal the pressure at this point, and the pressure at this point is equal to the atmospheric pressure. So that's basically the logic behind this. Let's see. So pressure of the gas, of course, is currently unknown. The pressure of 6 inches of mercury, we can calculate that later on. The atmospheric pressure is equal to 29.92 inches of mercury, so maybe I should work in inches of mercury for now. So pressure of gas plus 6.00 inches mercury is equal to the atmospheric pressure of 29.92 inches of mercury. Okay, subtract 6 inches of mercury on both sides. So subtraction, I just count decimal places, 2 decimal places for both, so we should still end up with 2 decimal places in the end. The pressure of the gas in here is equal to 29.92 minus 6.00 is 23.92 inches of mercury. Okay, and then we can convert that to atmospheres. I'm just going to use this for convenience so that I don't have to do it in multiple steps and go to centimeters and then millimeters and then atmospheres. I'll just go in one go. So 23.92 inches of mercury. If we convert that to atmospheres, we know from the problem that 29.92 inches of mercury is equal to 1 atmosphere worth of pressure. So let's go ahead and calculate that, and then we'll be pretty much home free. 23.92 times 1 over 29.92 is 0.7995. If we keep 4 sig figs, 0.7995 atmospheric pressure. And then of course you can convert easily from ATMs to whatever units the problem was asking for, torrs, pascals, and bars. I'm just going to skip that part because I'm assuming you have already figured out how to do it from previous examples. Okay, let me see. I have one more manometer example here. Do we want to do it? Let's have a look. So it says the pressure of a sample of gas is measured at sea level with an open-end mercury manometer. Assuming atmospheric pressure is 760.0 millimeters of mercury, determine the pressure of the gas in millimeters mercury, atmospheres, and kilopascals. And yeah, it's pretty much the same as the last problem, so I think we should just skip it. Yeah, gonna skip it, and let me see what I have lined up next. So now I think it's finally time to start talking about the gas laws. Actually, before I do that, let's talk about temperature real quick. Let's talk about the different temperature scales. You probably already know this, but couldn't hurt to refresh our memory for those who haven't learned or have forgotten. Might as well cover it. So we have 3 traditional temperature scales that we work with: Fahrenheit, Celsius, and Kelvin. So the Fahrenheit scale is only used in 2 countries. One of them is, of course, the United States, and the other one I don't really remember. Celsius is used pretty much everywhere else, and I don't know, I think Celsius is much more appropriate. But Kelvin is what we're going to be using when dealing with the gas laws. We're going to be using kelvins a lot in chemistry. Sometimes we'll be able to do problems with Celsius, but if you're in doubt, going with kelvins is a safe bet if you're not sure what you're doing. But yeah, in chemistry, we never, ever, ever work in Fahrenheit. For the Fahrenheit scale, we have the freezing point of water at 32 degrees Fahrenheit. The boiling point of water is 180 degrees above that, which is 212 degrees Fahrenheit. So that's the freezing point. And that's the boiling point. I probably should have done this in a different color. Or I can do that. On the Celsius scale, you've got 100 degrees Celsius is the boiling point of water, while 0 degrees Celsius is the freezing point. Much easier numbers to remember. And on the Kelvin scale, depending on who you ask, the freezing point of water is 273, or some people will say 273.15 or 273.16. For me, I'll usually just go with 273, but, you know. And the boiling point would be 373.15 kelvins. Again, I'm just going to use 273 and 373 in most cases. I can't really think of any cases where I would really bother to add that extra 0.15 because usually most problems don't give you more than 3 sig figs anyway. But yeah, the Kelvin temperature scale is also known as the absolute temperature scale. And the reason it's called the absolute temperature scale, well, remember absolute values from algebra? In the Kelvin temperature scale, 0 Kelvin is the lowest possible temperature in the universe. That's the definition of 0 Kelvin. So there's no such thing as negative Kelvin temperatures. And this is going to be very important when we're working with gases. Once we see the gas laws, we're going to see the problems that would come up if you allowed a temperature scale that gave you negative temperature values. It would result in something that's kind of screwy, and we'll get into it when we get into it. But the other thing you might notice is that the difference between the freezing point and boiling point of water in kelvins is the same as it is in Celsius. That is, it's a 100-degree gap. The size of a degree Kelvin is equal to the size of a degree Celsius. So later on, when we talk about things that depend on the change in temperature, if I talk about water warming up from, say, 15 degrees Celsius to 25 degrees Celsius, we would say it went up by 10 degrees Celsius in temperature, but you could also say that it went up by 10 degrees in Kelvin, because the size of a Celsius degree is the same as the size of a Kelvin degree. Also note that we don't actually use the degree symbol when working with kelvins, unlike with Celsius and Fahrenheit. And converting between Celsius and Fahrenheit, I guess I could go over it, but I don't see much point in doing that because, again, in chemistry, we never work with Fahrenheit to begin with, so I don't think there's a need to bother with converting between Fahrenheit and Celsius unless, you know, you have one of those teachers, in which case I think you can learn it on your own pretty well. So I'm just going to skip that part for now, or I guess you can Google Fahrenheit to Celsius conversion if you really need to know it, but I'm going to skip it. Anyway, with gas laws, we're definitely going to have to work in kelvins every single time. We'll see the problems that arise from not using kelvins pretty soon. In fact, I think we'll see it in the very first problem, or not first problem, but first gas law. Okay, so let's talk about the basic gas laws. First we've got Charles's law. Charles's law says that under constant pressure, the volume of a gas is directly proportional to its absolute temperature. So Charles's law says volume is directly proportional to temperature. So basically, volume is some constant times temperature, in other words. And I'm just using K for a constant because I think K is what people usually use for constants. But if volume and temperature are directly proportional, then the ratio of volume to temperature must be constant. So if I divide both sides by temperature here, then volume over temperature equals a constant value. So if I have the same gas, but I change its temperature, then its volume needs to change so that the ratio of its volume to its temperature stays at the same value of whatever this constant is. In other words, if I have some initial volume V1 at an initial temperature T1, and I decide to raise or lower the temperature and change the temperature to T2, then the volume has to change to V2 such that V2 over T2 is still equal to K, which is equal to V1 over T1. So kind of the same as what we did with, let me think. Actually, did we ever do any examples of an equation where we had I don't think we did anything that involved directly proportional quantities, so I guess this might be the first example of that. But we kind of did something similar when justifying the dilution equation, M1V1 equals M2V2. When we said that molarity times volume equals the moles of solute, which, when diluting, would stay constant because you're not adding or removing solute, but changing the amount of solvent. Kind of the same logic applying here, except this time that the volume and temperature are directly proportional, whereas with the dilution equation, volume and molar concentration were inversely proportional. But anyway, that's just a bit of a side note, which we can just kind of wall off into our subconscious memory. So V1 over T1 equals V2 over T2. Let's go ahead and take a look at what would happen if you allowed negative temperatures. If we allowed negative temperatures, then that would mean we'd have to have negative volumes. Imagine you have a gas with a volume of, I don't know, 2 liters at, let's say, 50 degrees Celsius. What is its volume? What is its volume at, say, negative 10 degrees Celsius? What would the volume be at negative 10 degrees Celsius? Well, if I just try plugging into the equation V1 over T1, so 2 over 50, without converting my Celsius to kelvins, then that's going to equal V2 over T2, so that's V2 over negative 10. This would mean, if I multiply negative 10 over to the left-hand side, then I get negative 20 over 50, so V2 would be negative 2/5. V2 would be negative 2/5, or negative 0.4 liters. That doesn't make sense. That doesn't make sense at all. So yeah, we do not want to use a temperature scale that allows negative values. Never, ever, 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 ever use any temperature scale other than kelvins when working with gases. only kelvins, well, the only known temperature scale would be kelvins for working with the gas laws. Anyway, I guess we could just solve this problem by converting the Celsius to kelvins and getting the actual answer, but we'll have plenty of examples of this later on, so I'm not going to bother with that one anymore. Next up, let's take a look at Boyle's law. Let's take a look at Boyle's law. So Boyle's law, to me, is the most intuitive of the gas laws because it says that the volume of a gas is inversely proportional to its pressure, assuming that you keep the temperature constant. So assuming that you keep the temperature of a gas constant, then by adjusting the pressure of a gas, the volume will change. If you increase the pressure, the volume will go down. If you decrease the pressure, the volume will go up. To me, that's pretty intuitive. If you squeeze a gas, you're, reducing its size, you're reducing its volume. So to me, Boyle's law is probably the most intuitive out of all of them. But yeah, so they're inversely proportional, which means pressure is equal to some constant times 1 over the volume. And of course, if I multiply the volume over to the other side, then I find that pressure times volume is equal to a constant. And whenever a product or ratio is equal to a constant, then that product or ratio before is equal to that product or ratio after. So P1V1 is equal to P2V2. If I have something with a volume of, say, 4 liters and a pressure of 2 atmospheres, for example. Let's say we have 4 liters and 2 atmospheres. And later on, I decide to decrease the pressure to 0.5. So I've reduced the pressure by a factor of 4. I have 1/4 of the pressure. I would have 4 times the size, 4 times the volume, so 16 liters. And of course, I'm ignoring my sig fig rules here, but that's just a quick, simple example. So that's Boyle's law. P1V1 equals P2V2. I should probably box these so that we know what to take away from each of these sections. But yeah, there's Boyle's law. Next up, we have what's called the Gay-Lussac law. This one is usually not mentioned in textbooks, and I don't know why. We've got Gay-Lussac's law, which says under a constant volume, the pressure of a gas is proportional to its absolute temperature. Absolute temperature is another way of saying Kelvin temperature. I know, I might be sounding like a broken record here, but I guarantee you one of the most common mistakes in this chapter is forgetting to convert your temperature to kelvins. Gay-Lussac's law, so basically pressure is directly proportional to absolute temperature. So that's another way of saying pressure is equal to some constant times the temperature. So then if I divide by temperature, pressure over temperature is equal to some constant, which means pressure over temperature before must equal pressure over temperature after. Again, under the condition that you keep the volume constant. So all three of these gas laws make an assumption that isn't explicitly stated, and that assumption is that you're working with a fixed amount of gas. You're working with a fixed number of gas particles, a fixed number of moles of gas particles. But of course, you can see changes in pressure, volume, and temperature if you modify the amount of gas that's in a gas container. Introducing Avogadro's law. Oh yes, Avogadro also gets a gas law. Avogadro's law. So Avogadro's law says that the volume of a gas is directly proportional to the number of moles. That's also fairly intuitive. The more gas particles you have, the greater their size. So volume is equal to some constant times the number of moles. If you double the moles, you double the volume. At least that's what you would expect. We'll talk about ideal gases versus real gases later on in this video. But yeah, so if I keep going with this, then volume over number of moles is equal to some constant, which means volume over number of moles before is equal to volume over number of moles after. And there you go, that's Avogadro's law. Let's keep on going. We've got more gas laws. There's a ton of gas laws in this chapter, and I think I'm going to list all or most of them right here. I think I might be saving a couple for later towards the end of the video. But let's see, so we did Charles's law, Boyle's law, Gay-Lussac's law, Avogadro's law. Now there's something that isn't often mentioned in chemistry classes, but it's called the combined gas law. The combined gas law. And the combined gas law is basically a combination of Charles's law, Boyle's law, and Gay-Lussac's law. If you just put all three of those gas laws together, then you end up with the combined gas law, which says P1 V1 over T1 equals P2 V2 over T2. And in fact, you might be better off, if you don't like memorizing too much, you might be better off just remembering the combined gas law, because the combined gas law reduces to Charles's law, Boyle's law, or Gay-Lussac's law by eliminating one of the three variables. So Charles's law said that volume and temperature are proportional as long as you're working under constant pressure. Well, constant pressure means that P1 is equal to P2, so you would just cancel it out. You would cancel it out on both sides, and you'd be left with V1 over T1 equals V2 over T2, which is Charles's law. You can do the same thing with Boyle's and Gay-Lussac's. So Boyle's law said pressure and volume are inversely proportional under constant temperature. If T1 is equal to T2, then they'll cancel out, and you'll be left with P1 V1 equals P2 V2. And of course, Gay-Lussac's law, same thing. Gay-Lussac's law says pressure and temperature are directly proportional under constant volume, so constant volume would mean V1 is equal to V2. They would just cancel each other out, and you'd be left with P1 over T1 equals P2 over T2. But of course, we can take this a step further. There is no official name for this one, but if you also throw in Avogadro's law, then you get this. P1 V1 over N1 T1, so now we're taking the number of moles into account, equals P2 V2 over N2 T2. So there's no official name for this, but I like to call it the super combined gas law. The super combined gas law. Again, not official terminology, so don't write this on your test because your teacher will have no clue what you're talking about. But yeah, I call this the super combined gas law. If you know this, then you can just eliminate whichever of the four variables are constant, and it'll always reduce down to just what you need and nothing more. So if you have a problem where the moles are constant, you can use this because the moles will cancel out. If you have a problem where the temperature's constant, you can cancel out the temperatures. Same thing for pressures when they're constant or volumes when they're constant. If you have two different things that are constant, you can eliminate both of those and just be left with the two variables that are changing. So yeah, if you don't want to memorize too much, then I would recommend this one because it reduces down to all of these other previous gas laws anyway when it needs to. And I do recommend doing some level of memorization even if your teacher gives you a formula sheet, because I see it all the time. I may have talked about this in a previous part, I don't remember. But memorizing formulas, memorizing equations is a good thing to get into the habit of doing, because when you're given a formula sheet, what I see students do all the time is they kind of just waste time looking for the correct formula. And when you have it memorized, not only do you know the equation, but you also know the situations that it's useful for. When you become overly dependent on a formula sheet, you start digging around through the formula sheet for whatever looks like it could work, and you just kind of go through the motions without really knowing what you're doing. So I don't really recommend becoming overly dependent on formula sheets. But yeah, that's my little tangent there. I go off on too many tangents, but as I stated in previous parts, I think these tangents are worthwhile. Where do we go from here? So I guess we can talk about something called the ideal gas equation. So this comes from what I call the supercombined gas law, I suppose. So if we look at this, what does this mean? So whenever, you know, the 1's are equal to the 2's on two sides of an equation, that means that this ratio or product is equal to some constant. So pressure times volume over number of moles times absolute temperature is equal to some constant. And this constant, instead of K, I'm actually going to call it R. So this value R right here is called the ideal gas constant, or just the gas constant. And it takes on different values depending on the units that you use for volume and pressure specifically. You don't really have much choice for N and T. N should be or ought to be measured in moles, while temperature is measured in kelvins, so those are locked in. But your pressure and volume units, you have lots of different options, you have lots of different choices. So this ideal gas constant was determined to be equal to 0.08206 liter atmospheres per mole Kelvin. Or, as I sometimes like to call it, latums per molk. It's cheesy, but it's an effective way to remember the units. Of course, if you do some conversions, then you'll also find that the ideal gas constant is equal to 8.314 cubic meter pascals per mole Kelvin. So whenever you're using cubic meters for volume instead of liters, this would be appropriate, and when you're using pascals instead of atmospheres. So that's another value of the gas constant. It's also equal to 8.314 joules per mole Kelvin. I'll explain what a joule is in a minute. And then it's also equal to 62.36 liter torrs per mole Kelvin. And I guess we can do a conversion to verify at least one of these. Just convert between one and the other. So let's do this one and this one. Let's convert the first version of the gas constant to the second version to show that they really are the same value, just expressed in different units. So we've got 0.08206 liter atmospheres per mole Kelvin. And we want to convert it to cubic meter pascals per mole Kelvin. So we need to convert the liters to cubic meters and the atmospheres to pascals. Atmospheres to pascals we already know. 1 atmosphere is equal to 1.013 times 10 to the 5 pascals. And then converting liters to cubic meters. So the definition of a liter is 1 cubic decimeter. 1 liter is equal to 1 cubic decimeter. So 1 liter is equal to 1 cubic decimeter, 1 decimeter cubed. Okay, and to convert cubic decimeters to cubic meters, you basically need to convert decimeters to meters 3 times. So if you remember your scientific prefixes, deci means 1/10. A decimeter is 1/10 of a meter, so what I need to do is say 1 decimeter equals 10 to the -1 meters, and then I need to do that 3 times, so do this cubed. So taking all of this and cubing it, that would cancel all 3 powers of decimeters and give me 3 powers of meters, or cubic meters in other words. So you could also rewrite this, and I'll just do it in a different color. You could also rewrite that as 10 to the -3 cubic meters for every 1 cubic decimeter. Can you even see that on the screen? Yes, you can. Okay. I try to avoid writing at the very bottom of the page, but every now and then I kind of feel forced. But yeah, let's go ahead and do this conversion and see what we get for it. So 0.08206 times 1.013 times 10 to the 5 gives me 8,313. Ooh. Kind of close. So I guess I should have included more digits here, but I'm getting 8,313, and that's in, let's see, liter pascals per mole Kelvin. And then of course, if you convert the liters to cubic decimeters and then the cubic decimeters to cubic meters, then you're multiplying that by 10 to the -3, which is 1/1000th, so you get 8.313 cubic meter pascals per mole Kelvin. So yeah, 8.313 is pretty close to 8.314, so I probably should have gone with 1.01325, just used the full thing here, and I probably would have gotten exactly 8.314 from that, but I think this is close enough to show you that these conversions or these different values for the ideal gas constant are totally legit. Completely legitimate. So the ones that you definitely need to remember will be this one and the 8.314, both versions of it, but especially this one. So cubic meter pascals would appear to be equal to joules. What on earth is a joule? Well, if you don't know your physics, then the most I can tell you about joules is that a joule is equal to a newton times a meter. A joule is the amount of energy that you give to an object if you apply a force of 1 newton on it while pushing it through a distance of 1 meter. If for 1 whole meter you push, say, a box with a force of 1 newton, then the amount of kinetic energy that you give to it is equal to 1 joule. So in other words, 1 joule is equal to 1 newton meter. Let me write that up here. 1 joule is equal to 1 newton meter. Okay, so if we unpack the pascals, remember at the very beginning, what was a pascal? 1 pascal was equal to 1 newton per square meter. Some of you already see where this is going, and some of you know your physics, so you knew where this was going a long time ago. But if a pascal is a newton per square meter and a joule is a newton meter, then cubic meter pascals, if I take cubic meters times pascals, which are newtons per square meter, then I can cancel out square meters with 2 powers of the cubic meter, leaving me with just meters. Meters times newtons, or newtons times meters. Oh, that's joules. And there you go. Very simple proof. But yeah, pressure times volume gives you units of energy. Pressure times volume gives you units of energy. That's gonna be brought up again in the next video when we talk about thermochemistry and the energy that is delivered to or from systems through pressure volume work, as we will call it. But that's for a later video. Just remember this for now. Remember that units of pressure times units of volume always give you units of energy. Liter atmospheres can also be viewed as units of energy, but of course the traditional or official unit of energy is the joule. And in chemistry, more often than not, we will deal with kilojoules rather than joules, so it might be helpful to know this in kilojoules per mole Kelvin rather than joules. Let me actually write that down. So if I convert it to kilojoules, it's going to be 8.314 times 10 to the negative 3 in kilojoules per mole Kelvin. .314 joules is 8.314 thousandths of a kilojoule. But yeah, so I guess I'll add that as well. So 3 different values of the gas constant that you definitely want to know. The 62.36 can be helpful, but you don't really need it because you can easily convert, if you're given torrs, you can easily convert that to atmospheres and just go back to using this one anyway. So it's up to you. I'm going to use it for convenience from time to time because I actually do have it memorized, but you don't need to remember it. As long as you remember this one and you know how to convert your pressures to atmospheres, you'll be good to go. Your volume will usually be given in liters because they don't expect you, I guess, to know that a liter is a cubic decimeter. I think it's a really simple and easy fact to teach, but chemistry courses don't emphasize it. So the only way that you would know it is if you specifically looked it up, I guess, or did the calculation yourself. But now I'm rambling too much. Let's take a look at... Wait, there was one more thing, wasn't there? Oh, right. The ideal gas equation. So over here, so this equation right here, can be rearranged to give us the ideal gas equation. Let's do that on the next sheet. The ideal gas equation. The ideal gas equation. It's simply a rearrangement of that equation that I just had on the previous sheet. So we said that the ratio PV over NT is constant, and we give that constant a special name. It's the ideal gas constant. If we multiply the NT over to the right-hand side, then we get PV equals nRT. Pivnert. This is known as the ideal gas equation. So this will work for any gas under any circumstances as long as you treat it like an ideal gas. And we'll talk about the differences between ideal gases and real gases later. But for now, let's assume all the gases we're working with behave ideally. If that's the case, then this equation will always work. So I would strongly recommend, if you're not going to memorize everything, commit this to memory and commit this to memory. Well, basically, I guess you could say this comes from this, but, you know, remember the super combined gas law and the ideal gas equation, and you should be good to go. Now, if we solve the ideal gas equation for the ratio of volume to number of moles, if we rearrange the ideal gas equation to find the ratio V over N, then what we end up with is something called the molar volume of a gas. So I guess V over N, that part stays, and then it looks like I need to multiply the, I'm starting from here, multiply the temperature and divide the pressure over to the other side, so that would be RT over P. Okay. So RT over P is equal to V over N. V over N is what's known as the molar volume of a gas. Molar volume of a gas. It's liters of gas, ideal gas, per mole of ideal gas. This is going to be helpful with stoichiometry. Let's figure out what the molar volume would be under standard temperature and pressure. We abbreviate that STP. STP is standard temperature and pressure. Temperature and pressure. Okay. So the standard temperature and pressure for the gas laws, at least, the standard temperature would be 0 degrees Celsius or 273 Kelvin, 273.15 if you really want to be particular about it. So 273 kelvins, and pressure is equal to exactly 1 atmosphere. So those are standard conditions when dealing with ideal gases. Some people use a different definition here. Some people still keep the same temperature, but instead they use a pressure of 1 bar, which is a little bit less than 1 atmosphere. But this is what we are going to go with, so we will use this as our definition of STP. But there are people who use 1 bar as the standard pressure, so definitely make sure you ask and clarify what you mean when you do standard temperature and pressure in your class. because I think it was decades ago that they actually did redefine standard pressure to be 1 bar, but schools still use 1 atmosphere for academic purposes, I suppose. Not really sure why. Well, actually, I think I can guess why. Because if you're using the ideal gas constant as liter atmospheres per mole Kelvin, I guess it would be pretty intuitive to use 1 atmosphere for the standard pressure. Yeah, that might be it. It's just a time-saving measure. Anyway, what is the molar volume under this first version of standard temperature and pressure? Well, let's go ahead and calculate it. So V over N is equal to ideal gas constant. So I want my volume to be in liters, so I'm going to use 0.08206, which is in liter atmospheres per mole Kelvin, and I'll write out the units just so we can follow along and see that they actually do work out the way they're supposed to. Per mole Kelvin. Multiply that by the standard temperature, which is 273 kelvins. And then divide that by the pressure. The standard pressure is 1 atmosphere. So under standard conditions, the molar volume is equal to, let's see, so kelvins cancel out with kelvins, atmospheres cancel out with atmospheres, and you're left with liters per mole, which is what we want. So 0.08206 times 273 divided by 1 is about 22.4. Equals 22.4 liters per mole. So that's under standard temperature and pressure. What about non-standard temperature and pressure? Well, just use this equation and again plug in whatever your non-standard temperature is, plug in whatever your non-standard pressure is, and get your molar volume for whatever temperature or pressure conditions you have. But since standard conditions are pretty common, it would be advantageous to remember that under standard conditions, 22.4 liters is the volume of 1 mole of any ideal gas. Of course, if you use 1 bar as your standard pressure, let's see how that plays out. I'm kind of curious because I remember having done it once, and I remember the number came out to be rather special. But yeah, let's see. So if I do, I'm not going to write out the units this time, 0.08206 times 273 still, over 1 bar. So 1 bar, if I convert it to atmospheres, then let's see, 1.013 bars is equal to 1 atmosphere. So if I divide by that, so 1 over 1.013 is 0.987 approximately, about 0.987. That's 1 bar converted to atmospheres. If I do that, 0.08206 times 273 divided by 0.987 is 22.7. I remember it being something more unique than that, but okay. 22.7 liters per mole. What was it that I noticed in this number the last time I calculated it? I can't seem to remember. Oh well. But yeah, under our definition of standard conditions, where the standard pressure is 1 atmosphere, we're going to use 22.4 liters per mole to be the ideal molar volume. So this ideal molar volume is actually quite useful. You might actually remember the term molar volume from a previous video, because we did talk about this. I think it was in video number 3. You might recall this flowchart that we put together, and I did mention that there was another way to go from liters to moles of something, and that's to use the molar volume of a gas. So that's what we're going to look at. Let's do a quick example of it. Let's go to one of my favorite examples involving gases, the formation of ammonia, or nitrogen trihydride. So let's take nitrogen gas plus hydrogen gas forming ammonia. If I balance this equation, then I'm going to need a 3 here and a 2 here, and I'm done. Okay, so now that I have this balanced equation, let's say that this reaction happened under standard conditions. Let's say I was asked for moles of NH3 produced, so moles of NH3 produced from the reaction of, let's say, 15.6 liters of hydrogen gas in excess, 15.6 liters of hydrogen gas with excess nitrogen gas. If I reacted 15.6 liters of hydrogen gas with excess nitrogen gas at STP, at standard temperature and pressure, which for us means 273 kelvins and 1 atmosphere, then how many moles of ammonia are produced? And also, I guess, how many liters? So how many moles and also how many liters of ammonia are produced? So let's see, we've got 15.6 liters of hydrogen. 15.6 liters of hydrogen gas is equal to, or sorry, is converted to moles by using the fact that under standard temperature and pressure, 22.4 liters of a gas is equal to 1 mole of that gas. It doesn't matter what the gas is. This is true for all gases under the same temperature and pressure conditions. If the temperature and pressure conditions change, then this number down here will change, and you'll have to calculate it using this equation again, but otherwise you can, once you've found it, you can apply it to all the gases in that particular problem. But yeah, so now that we've got, I should probably write H2, for every 3 moles of H2 we get 2 moles of NH3. I think I said I was going to stop writing these, but I'll get to that eventually. I'll stop writing them. I guess it's become too ingrained as a habit at this point. Let's see, and then converting moles of NH3 to liters of NH3, we just use the same conversion factor again. So every 1 mole of ammonia gas is equal to 22.4 liters. And you might notice something here, which is that these two conversion factors basically cancel each other out. That does actually make sense. Under the same temperature and pressure conditions, the ratio of moles of gas is equal to the ratio of their volumes. If the temperature and pressure are constant, well, that's Avogadro's law. Volume over moles is equal to volume over moles for whichever gas you're working with. So it does actually make sense. You could take a bit of a shortcut if you realize that, but let's work this out. So 15.6 liters, 15.6 over 22.4 is 0.696. So that's 0.696 moles of hydrogen gas. And of course, if we multiply that by 2/3, 0.696 times 2/3, I can do this without a calculator. That would be, let's see, 0.464 moles of NH3. And of course, if we go and multiply that by 22.4, then 0.464 times 22.4 is 10.4 liters, is equal to 10.4 liters of ammonia gas. Okay, let's see, what was I going to say here? Oh, right, let's try calculating the volumes more directly. Let's try calculating this volume directly just based on these ratios. So the idea here is that as long as the pressure and temperature for all three gases in this equation are fixed, then the volume will just be proportional to the number of moles. So basically this equation is saying for every 22.4 liters of nitrogen gas that react with, let's see, well, I'm overthinking this. For every 1 liter of nitrogen gas and 3 liters of hydrogen gas, you produce 2 liters of ammonia gas. And of course, you can scale that up to whatever number of liters you actually have for whichever for whatever your limiting reactant is supposed to be. I can't talk today. This is what happens when I try to talk too fast. Maybe I should slow down. Okay, so if I follow that logic, then for every 3 liters of hydrogen gas, I get 2 liters of nitrogen gas. So if I just start from 15.6 liters, then I can say and that's 15.6 liters of hydrogen gas. So for every 3 liters of hydrogen gas, I get 2 liters of ammonia gas. And if I just do that quick conversion, I should still get 10.4. 15.6 times 2 over 3. Yep, 10.4 on the dot. 10.4 liters of ammonia. So yeah, 2 different ways of going about it. You can do the full dimensional analysis process, or you can take note of the fact that under constant temperature and pressure conditions, whether they're standard temperature and pressure or non-standard temperature and pressure, the volume ratios are equal to the mole ratios in a balanced chemical equation, so you can just work directly with volumes if you don't actually need to calculate moles or grams or anything like that. Okay, I think we need to do one more thing before we start looking at example problems, which is the density form. Oh, actually, maybe two more things. The density form of the ideal gas equation and Dalton's law of partial pressures. And I guess mole fractions. Okay, so we've got a couple more things to do. We've got a couple more things to do. What is that? I don't know, I'm just going to ignore it. Or I guess I can, yeah, flip to the other side of the paper so it doesn't bother me. Okay, so density form of the ideal gas equation. First, let's write out our ideal gas equation, PV equals nRT. And let's see, so there is some use for this equation in determining the density of an ideal gas based on its molar mass. And here's how we derive the equation that helps us do that. So density, as you know, is mass over volume. At least that's what density means in chemistry. In physics, there are different types of densities. I talked about this before, so I'm not going to state it all again. But in chemistry, density usually means mass volume density. So we're talking about the mass per unit volume. So mass per unit volume can be something like grams per liter, or kilograms per cubic meter, or any mass unit per any volume unit. In our case, we want the density of a gas in grams per liter. So how do we get that? Assuming pressure is still in atmospheres, let me actually write that in a different color. So assuming we have our pressure in atmospheres, and our volume in liters, and our N in just moles, and the ideal gas constant is just going to be liter atmospheres per mole Kelvin, and our temperature, of course, is going to be in kelvins. We can determine the mass of a gas by simply taking the number of moles and multiplying it by the molar mass, right? If I know the moles of a gas and I know the molar mass of a gas, then I can multiply that. Moles times molar mass, which I will represent with a curly M. So this is molar mass in grams per mole. Later on, I'm going to show an equation that uses kilograms per mole for the molar mass, but we'll get to that when we get to that. But yeah, number of moles times the grams per mole. Moles would cancel out and you'd end up with grams. You would end up with mass in grams. So mass in grams. Okay, and once you've got the mass in grams, you can get the mass in grams per liter by just dividing by the number of liters. So let's go ahead and do that to our ideal gas equation. I'm going to multiply both sides by the molar mass first. So I'm going to multiply PV curly M equals curly M times nRT. Curly M times N, well, that's just the mass. So PV molar mass is equal to actual mass in grams times RT. Divide by the volume. So we get pressure times molar mass is equal to mass over volume times RT. And what's mass over volume? Well, that's density. So P curly M equals dRT. Remember this, because I don't think you're going to remember the derivation. You'll be better off remembering this final equation right here. PivNert can be converted into PimDirt. Again, a cheesy, silly pronunciation, but trust me, it does help with remembering the equation. Pivnert turns into Pimdirt. Or maybe, if I write the M first, I could call it mop dirt, because you mop dirt off the floor, I guess. Well, I don't think a mop would be the most effective thing for removing dirt, but whatever helps you remember it is my point. It doesn't matter how cheesy it is. But yeah, so pressure in atmospheres times molar mass in grams per mole, which is what it usually is, equals density, this is going to be in units of grams per liter, times the ideal gas constant times the temperature. So studying this equation can actually help you explain certain things, like how hot air balloons work. So if you solve for density, if I rearrange this and solve for density, then I find density is equal to, so divide by R and divide by T, so you're left with P m over RT. R is just a constant, so it's not going to change. If you increase the pressure of a gas, you increase its density. That kind of makes sense. If you squeeze a gas more tightly, then you're packing the mass into a smaller space, so to speak. If you use a gas that already has a higher molar mass, it'll have a higher density. That also makes sense, right? I would expect oxygen to weigh more than hydrogen because oxygen has more molar mass than hydrogen. And then for temperature, it looks like the higher the temperature, the lower the density. Think about that when thinking about how hot air balloons work. Gases with lower density tend to float up, while gases with higher density tend to go down. You can learn how to calculate the exact amount of force that these density differences create if you study Archimedes' principle in physics, but we're not doing physics today, so maybe I'll cover that in a different video if I ever decide to do a series on physics. I don't know if I need to, because there are already plenty of good YouTube videos for physics. It's just chemistry. I've looked around and I can't find anything that's really all that good. Like, I find a couple of good videos out there, and the problem is they don't cover all the topics, or they don't cover all the topics extensively enough for my liking. And yeah, that's one of the main reasons why I'm doing this, is because I feel that there isn't a really good comprehensive chemistry series out there yet. Went off topic again and forgot what we were doing. So we derived the density form of the ideal gas equation. We will put that to use in some of the problems we'll be seeing soon. Two more things. What were they? Dalton's law of partial pressures and mole fractions. Okay, so let's suppose I'm going to wall off all of this. Let's suppose we've got a container. So just a closed box, and it's got a bunch of different gases in it. So let's say we've got some, let's see, 1, 2, 3, 4, 5, 6, 7, let's say 8, 9. Let's say we've got 9 particles of oxygen gas in there. So that's O2. And let's say we also have something that won't react with oxygen. So let's just use the noble gases, neon and helium. Let's use neon and helium. So I'll use, let's say I've got 1, 2, 3 particles of helium in there. And let's suppose I've got myself 6 particles of neon. 1, 2, 3, 4, 5, 6. So that's neon. Okay, so 9, 3, and 6. We've got 9 oxygen, 3 helium, and 6 neon in this container. Now, let's say that I attach a pressure gauge to this container. Let's say I attach a pressure gauge. And let's say it measures a pressure of, let's say 24 atmospheres. Let's say the pressure gauge says that the total pressure inside this container is 24 atmospheres worth of pressure. Well, the pressure is going to be proportional to the number of moles. The more moles of a particular gas you have, or the more moles of gas you have in general, the higher the pressure. If you keep the volume constant and you keep the temperature constant, and you already know that the ideal gas constant is constant, it's in the name. If I keep those three things constant, then if the number of moles of gas in a container goes up, then the pressure should also go up. That's the only way this equation would continue to function. So in fact, maybe there should be another gas law for P1 over N1 equals P2 over N2. But again, what I said earlier about this super combined gas law, as I like to call it, is that you can just eliminate the variables that are constant and it'll work for whatever situation you have to deal with. So when volume and temperature are constant, they just cancel out on both sides, and you're left with P1 over N1 equals P2 over N2. So we had it all along. But yeah, so more moles of gas means more pressure, and assuming that the gases are ideal, all the gas particles are going to behave identically regardless of their identity, regardless of whether it's oxygen or helium or neon. So the amount of pressure that each gas supplies is just proportional to the amounts of particles of that particular gas, the number of moles of that particular gas in the mixture. Over here I've got a total of 9 plus 3 plus 6, 18 moles or 18 particles of gas. Let's say each one of these circles represents a mole. So I've got a total of 18 moles of gas, and oxygen represents half of that. So the mole fraction of oxygen, we represent mole fractions with a capital X. The mole fraction of oxygen is the moles of oxygen over the total moles, And can you see that? Barely. Let me push it up a bit. Okay, now you can see it. So moles of oxygen over total moles in the container, in this case would be 9 over 18, which is equal to 1/2. Now you see why this is called a mole fraction. Through similar calculations, we see that the mole fraction of helium, it's 3 out of 18 moles, so mole fraction of helium is equal to 3 over 18, which reduces to 1 over 6. It's 1/6. And then the mole fraction of neon is 6 out of 18, that's 1/3. And of course, your mole fractions should add up to 1. 1/2 plus 1/6 plus 1/3 ought to add up to 1. Otherwise, you've overestimated the mole fraction for at least, overestimated or underestimated the mole fraction for at least one of your gases. But yeah, that's mole fraction. I know I mentioned mole fraction before when we were talking about concentration. And yeah, this is a type of concentration. It's the amount of what you want, the part of the mixture you're interested in, divided by the overall mixture, divided by the amount of overall mixture. So moles of oxygen over moles of the whole entire gas, that is a type of concentration. But yeah, so these mole fractions actually allow us to calculate the partial pressures of these three gases. Each gas has its own partial pressure, its own contribution to this total pressure of 24 atmospheres. If the oxygen is half of the gas in this container, then it's responsible for half of the pressure. So it's responsible for half of the 24 atmospheres of total pressure. So the oxygen's partial pressure must be half of 24, 12 atmospheres. So partial pressure of oxygen is 12 atmospheres. If I look to helium, helium is 1/6 of all of my gas particles, so helium must be responsible for 1/6 of the total pressure. The partial pressure of helium is equal to 1/6 of the total pressure. 1/6 of 24 is going to be 4 atmospheres. And then for neon, I guess I'll write it over here, I'm running out of room. Partial pressure of neon. Neon is 1/3 of all the gas in the container, so it must be responsible for 1/3 of the total pressure. 1/3 of 24 is 8 atmospheres. 8 atmospheres. So, Dalton's law of partial pressures, which I should write probably on another sheet, would be for the best. Dalton's law of partial pressures is very, very simple and intuitive. You probably don't even need to memorize this if you just understand it intuitively. You can just kind of common sense your way through it. The total pressure is equal to the sums of the pressures of gas number 1 plus gas number 2 plus gas number 3 and so on for however many gases you've got in your container. You just add up the partial pressures of all the individual gases. And then, of course, for the individual contribution of each gas, if you know the total pressure and you know the mole fraction of a gas, then you can say that the partial pressure of gas A is equal to the mole fraction of gas A times the total pressure, which is basically what I did back here, right? When I calculated the 12, 4, and 8, partial pressure of oxygen was the mole fraction of oxygen, 1/2, times the total pressure of 24. 1/2 times 24 gave me 12. And similar reasoning applied to the helium and neon. So yeah, partial pressure of a gas equals mole fraction of a gas times total pressure. I guess we can write this out further. The mole fraction of a gas is the moles of that gas over the total moles. And of course, if we multiply that by total pressure and then rearrange this equation by dividing both sides by the number of moles of gas A, then what we end up with, and this isn't something you need to know, but it kind of just helps with the intuition. We get partial pressure of gas A over moles of gas A equals the total pressure of all the gases over the total moles of all the gases. And there we have it. So P over N equals P over N. That's going to be the case if you hold the volume and temperature constant. Okay, and now I think with that we are ready to look at a bunch of problems using all of these basic gas laws. Maybe for pacing purposes I should have actually covered these problems bit by bit, but at least now I know that whatever we encounter we'll have already covered how to do it, or we'll have at least covered the equations needed to do it. Let's take a look. So, first up, number 27 says a spray can is used until it is empty, except for the propellant gas, which has a pressure of 1,344 torricellis at 23 degrees Celsius. If the can is thrown into a fire, which is at a temperature of 475 Celsius, what will be the pressure in the hot can? Okay, so since we're talking about a can, and we can assume the size of the can doesn't change, we can assume the can is rigid so it won't expand. A little bit unrealistic because we've seen cans expand and get crushed and explode and stuff, so not entirely realistic, but let's say it's one of those really rigid cans that's hard to crush or stretch or expand. Then we can assume the volume is constant. Basically, the other reason you can assume the volume is constant is because they don't mention it, nor do they mention anything that would help you determine the volume anyway. So that's kind of the rule of thumb with these problems. If something isn't mentioned, you can assume it's constant. They don't mention the amount of gas either, so you can assume constant moles. But yeah, so it looks like pressure initial is given, temperature initial is given, temperature final is given, and we need pressure final. Okay, that should be easy enough to do. So let me switch over to yellow. I'm kind of waiting for this yellow marker to die. I'm amazed that it has lasted as long as it has. But yeah, we've got P1 equals 1344 torrs. P2 is unknown. T1, they gave it to us in Celsius. It's 25 degrees Celsius, or no, 23 degrees Celsius. 23 degrees Celsius. If I want to convert that to kelvins, well, I know that 0 Celsius is 273 kelvins, so all you have to do to convert between Celsius and Kelvin is to add or subtract 273, depending on which way you're going. I'm going to add 273 here, and that would give us 296 kelvins. And then T2, let's see. So they said the final temperature is 475 Celsius. If I add 273 to that to convert it to Kelvin, so that's degrees Celsius. If I convert that to Kelvin, 475 plus 273 is 748. 748 kelvins. Okay, and now we have everything we need. So, again, if you don't want to memorize all of the smaller gas laws, you can just start with the super combined gas law. P1V1 over N1T1 equals P2V2 over N2T2. This is all you ever have to use for these types of problems. So I know the volume is constant. So volume on this side equals volume on this side. They cancel out. Number of moles is constant, so those cancel out. So you're left with the Gay-Lussac law. P1 over T1 equals P2 over T2. So 1344 torrs, I should probably include that, over T1 is 296 equals P2 over 748. So if I go ahead and multiply 748 over to the left-hand side, we've got 1344 over 296. Oh, and I forgot to write the units here, didn't I? Well, I mean kelvins. So the units of kelvins will cancel out on both sides, but this just goes to show that the final pressure we calculate will come out in torrs, and not atmospheres or pascals or anything like that. Anyway, 1344 over 296 is 4.54, and then 4.54 times 748 is 3,395.92. I'm going to have to round that to 3,400. I'm going to have to round that to 3,400. So P2 equals 3,400 torrs. And I need to show that I have 3 sig figs, so I would write this as 3.40 times 10 to the 3 torrs to be on the safe side. Alright, so that was the first one. Let's take a look at another. What is the temperature of an 11.2 liter sample of carbon monoxide at 744 torrs if it occupies 13.3 liters at 55 degrees Celsius and 744 torrs? Okay, so this one does not mention moles, so you can assume the moles are constant. Again, start with P1 V1 over N1 T1 equals P2 V2 over N2 T2. Thought I forgot something on that last page and had to double check it. Okay. So number of moles appears to be constant. Whatever the number is, it's going to be the same on both sides, so it's going to cancel out. And then we're left with P1 V1 over T1 equals P2 V2 over T2. So we are given 11 point, what's the temperature of an 11.2 liter sample? So I guess V2 is going to be 11.2. I guess I'm just going to start plugging the numbers in. So let's see, what is the temperature? So I'll call it T1 is our unknown. What is the temperature of an 11.2 liter sample? So V1 is 11.2 liters of carbon monoxide at 744 torrs. So pressure 744 in torrs. Gotta be really careful with the units here, because sometimes they'll give you mixed units and you're going to need to do some conversion to get the units to match up. If it occupies 13.3 liters at 55 degrees Celsius and 744 torr. Oh, well, how about that? The pressure is also constant in this problem. The pressure is also constant. So they said 13.3 liters at 55 degrees Celsius. Convert that to kelvins. 55 plus 273, that would be 328 in kelvins. So it looks like the pressure also cancels out. So and the volume 2 was given in liters. That's 13.3 liters. Okay, so the liters are going to cancel out. That's perfect. And so we get T1 in kelvins as we should. Okay, so I'm going to do 13.3 over 328. Actually, wait. No, it would be better to, so if I cross multiply this, I'm going to do 11.2 times 328. 11.2 times 328 equals 13.3 times T1. So 11.2 times 328 is 3,673.6. Rounding to 3 sig figs, that would be 3670, where the 0 does not count. So we get 3670, or 3.67 times 10 to the 3, equals 13.3 T1 divided by 13.3. So 3670 divided by 13.3 gives me roughly 276. Gives me T1 equals 276 kelvins. Okay. What do we have next? 2.5 liter volume of hydrogen measured at -196 Celsius is warmed to 100 Celsius. Calculate the volume of the gas at the higher temperature. Assume no change in pressure. I'm wondering if you cool down hydrogen that much, does it stay as a gas? Apparently yes. But I guess that's another thing I forgot to mention about Charles's law. I think I should talk about that right now before we do this problem. So something I forgot to mention about Charles's law. It said that volume over temperature is constant. V1 over T1 equals V2 over T2. So, of course, what this means is the higher the temperature, the higher the volume, and vice versa. In fact, I think this point that I'm about to make will make more sense if we write it the way I originally did, which is volume equals a constant times the temperature. Again, assuming the temperature is in kelvins. So, what is the volume of a gas at a temperature of 0 kelvins? Does it achieve a volume of 0? Because if I have a gas that has a volume of, let's say, 3 liters at 100 Kelvin, then at 200 Kelvin, it'll have a volume of 6 liters. Right? Directly proportional. So if the temperature goes up, then the volume scales with the temperature, but if the temperature goes down, the volume should scale with the temperature as well. But what happens if the temperature goes all the way down to 0? Does the volume of the gas become 0? The answer is no, and the reason is because you're not going to have it stay as a gas by the time it reaches a temperature of 0. You're not going to get a gas at 0 kelvins. If you cool it enough, it will eventually turn into a liquid, and if you cool it further, it'll probably turn into a solid. So the gas laws wouldn't apply if the gas has a phase change, which it most definitely will if you cool it enough. So yeah, that was a side note I forgot to mention when talking about Charles's law, but there you go. Let's look at that problem again. So it was a volume at a temperature, change the temperature, calculate the new volume. Okay, so we're using Charles's law. 2.5 liters is V1. T1 we need to convert to kelvins. And then T2 we also need to convert to kelvins, and we need to calculate V2. Okay, got it. So we've got V1 over T1 equals V2 over T2 equals V2 over T2. V1 is 2.50 liters. T1 is -196 Celsius. If I add 273 to that, then let's see, that would give me, I believe, 77. 273 minus 196, yeah, 77 kelvins equals V2 over 100 Celsius, that's 373 kelvins. I guess for this problem it would have been useful to actually have the 0.15, but I'm going to continue without it and just round our final answer to 2 sig figs. So the kelvins cancel out, and the volume should come out in liters. So 2.50 over 77 is 0.032. 0.032 times 373 is 11.936. Rounded to 2 sig figs, that would give me V2 equals 12 liters. Okay. And of course I could have started this the same way I started the other two problems with the super combined gas law, but if you know the smaller gas laws, then it saves time to just skip over crossing out the terms that are constant. Let's see, is number 30 anything interesting? A balloon inflated with 3 breaths of air has a volume of 1.7 liters. At the same temperature and pressure, what is the volume of the balloon if 5 more same-sized breaths are added to the balloon? Okay, that is kind of interesting. I don't know how someone could breathe accurately enough to make every breath the same volume of gas, but you know, we'll work with it. We'll play along. Very interesting. So the breaths of gas, you could say, are kind of like the moles of gas. They're about the number of particles of gas at the end of the day. So I'm going to treat breaths the same way I treat moles. That is, I'm going to use N to represent breaths, and then I guess, let's see, if we eliminate pressure and temperature, we're left with volume over moles, or in this case, volume per breath rather than volume per mole. So V1 over N1 equals V2 over N2, where N, in this case, instead of using numbers of moles, we'll use numbers of breaths. And if that doesn't sound intuitive to you, then assume that 1 breath is equal to 1 mole of gas. And, you know, even if it's not equal to 1 mole of gas, whatever number of moles it is, it's just some constant number, some sort of constant number times 1 mole. And you'd have that constant number on both sides, so it would cancel out anyway. But yeah, V1 over N1 equals V2 over N2, so 1.7 liters over, what was it, 3 breaths? Yeah, over 3 breaths, and I guess you're counting the breaths, so 3 is an exact number here. And then, what is the volume if you add 5 more breaths? Be very careful about this. N2 is not 5, it's 8. It's the total number of breaths, which is now at 8. Okay, so 1.7 over 3 and then times 8, so 1.7 over 3 is 0.57. 0.57 times 8 is going to be 4.6. So V2 is 4.6 liters. Okay, quick but rather strange problem. Let's look at another one. 31. A weather balloon contains 8.80 moles of helium at a pressure of 0.992 atmospheres and a temperature of 25 Celsius at ground level. What is the volume of the balloon under these conditions? Okay, so number 31 doesn't give us multiple pressures or multiple volumes or multiple temperatures because we don't have a changing pressure, volume, temperature, or number of moles. In this case, you want to use the ideal gas equation. In this case, you want to use the ideal gas equation. So let's do that over here. I think that's going to be the last problem I can fit on this page before we need to move to another page. So it said, let's see, let me write down my ideal gas equation first. So PV equals nRT. So we were given a pressure of 0.992 atmospheres. 0.992 atmospheres times a volume of, or was the volume unknown? Yeah, the volume is what we need to solve for, so V2 equals 8.80 moles times ideal gas constant times temperature. So it looks like if my pressure is in atmospheres and I want to get my volume in liters, it looks like I should just use 0.08206 liter atmospheres per mole Kelvin for my ideal gas constant for this problem. And then the temperature, they gave it in Celsius as 25 degrees. That's 298 in kelvins if you add 273 to it. 25 plus 273 is 298. I guess I should have written inside the parentheses Kelvin. But yeah, the kelvins in here will cancel with the kelvins in there, and the moles in there will cancel with the moles in there, and the atmospheres here will cancel with the atmospheres there, and that just leaves liters. So we will get V2 in liters. Okay, let's multiply everything on the right hand side first. So I've got 8.80 times 0.08206 is 0.722. 0.722 times 298 is 215. So we've got so far, and I guess I'll write it up here, we've got 0.992 times V2 is equal to 215, and then 215 over 0.992 is equal to 217. So V2 is equal to 217 liters. I guess I should have circled my answers for all the previous problems too. But yeah, there we go. V2 is 217 liters. Alright, let's look at another one and see if we get anything interesting. So 32, the volume of an automobile airbag was 66.8 liters when inflated at 25 degrees with 77.8 grams of nitrogen gas. We're doing stoichiometry. What was the pressure in the bag in kilopascals? Okay, I think I'm going to skip the pressure conversion part at the end, but at the very least I do want to do the stoichiometry part of this. Let's do some stoichiometry. Okay, so we are given 77.8 grams of nitrogen gas. 77.8 grams of nitrogen gas. And it reaches a volume of 66.8 liters. Oh, I guess you could use the... Yeah, you could. You could just use the density form here. You don't have to do stoichiometry. Okay, you can use the density form of the ideal gas equation. So that's going to be your mass. Volume is 66.8 liters. And temperature 25 Celsius or 298 kelvins. And we need to calculate the pressure. Okay, this this wasn't as interesting as I thought it would be, because you don't actually have to do stoichiometry. You can just use the density form of the ideal gas equation. Pm equals dRT. We can get d because it's the mass over the volume. So in this case, 77.8 over 66.8. So pressure is unknown. Molar mass of nitrogen gas we can calculate in a minute. Density is going to be 77.8 grams over 66.8 liters. Ideal gas constant, since we're working with liters already, I can get atmospheres for the pressure if I use 0.08206 liter atmospheres per mole Kelvin. I'm going to squeeze it in here per mole Kelvin. And then for temperature, temperature, I guess I'm going to have to write on a new line, is 298 kelvins. So temperature cancels out, the moles will cancel out once I get the molar mass. So molar mass of nitrogen gas, if I look at my periodic table, 14.007 is for one atom of nitrogen, so if I multiply that by 2, 28.014. 28.014 grams per mole should be the molar mass of nitrogen gas. So let's see, grams cancel with grams, moles in the denominator cancel with moles in the denominator of the gas constant, kelvins in the numerator for the temperature cancel with kelvins in the denominator of the gas constant. Liters here cancel with liters there, and yeah, your pressure should come out in atmospheres. Normally I wouldn't do this careful crossing out of units that actually cancel, but you know, just to make it extra clear for the people who haven't mastered the intuition of working with these units, eventually I would expect you to get better at realizing what units would come out of these equations when you use them, but that only comes with practice. So for now, it's good to include them. I guess calculation time, and you can solve for the pressure. You'll get the pressure in atmospheres, and then you can convert it to kilopascals. Yeah, I think I'm going to skip that part. I think I've covered the main part of this problem. You already know your sig fig rules, you know how to number crunch, so I'll leave that part to you. What's next? How many moles, so 33, how many moles of gaseous or gaseous, both pronunciations are correct, but I don't know, I feel that gaseous comes off as a little elitist. But maybe that's just my perception of it. Anyway, how many moles of gaseous boron trifluoride are contained in a 4.3410 liter bulb at 788.0 kelvins if the pressure is 1.220 atmospheres, and how many grams of boron trifluoride? Okay, so they want moles and they want grams. They gave us volume, temperature, and pressure. And they only gave us one of each of those. So, ideal gas equation again. No combined gas equation, no Boyle's law or Avogadro's law or Gay-Lussac's law or anything like that. Just PV equals nRT for this one. I think this is going to be another one of those where I set it up but don't fully solve. So PV equals nRT, we've got a pressure in atmospheres of 1.220. volume is 4.3410. More sig figs than what we'll have in the end. Equals number of moles is something they ask to solve for. Since we've got atmospheres and liters, we're using 0.08206 liter atmospheres per mole Kelvin. This is actually the value of the gas constant that you'll use most often in this chapter, but you do need to be aware of other values of the gas constant, especially when we get to the thermodynamics chapter, which is going to be much, much later. Next time we're going to be doing thermochemistry, which is not the same as thermodynamics. But yeah, keep that other value of the ideal gas constant, the 8.314 version, in the back of your head, because we will encounter it and we will need to use it eventually. Temperature, 788.0 kelvins. And yeah, so kelvins will cancel out. Kelvins will cancel out. Moles, that's what we're going to need to get. Atmospheres will cancel out. Liters will cancel out. And yeah, that assures you that you're going to get moles for N, as you should. And yeah, you can just crunch those numbers on your own and get the number of moles. To get the number of grams shouldn't be too hard. Once you have the moles, multiply by the molar mass of boron trifluoride. And you can determine the molar mass using your periodic table, of course. Let's move on to the next problem. 34 says iodine is a solid at room temperature but sublimes, so straight from solid to gas without turning into a liquid. When warmed up, what is the temperature in a 73.3 milliliter bulb that contains 0.292 grams of iodine vapor at a pressure of 0.462 atmospheres? Okay, so 34 is very similar to 32, because you've got the grams and you've got the milliliters, which you can easily convert to liters, so you can divide those and get your grams per liter. And once you've got your grams per liter and you get the molar mass from the periodic table, all that would be left to do is calculate, I guess in this case, the temperature given the pressure. So you would just use the density form of the ideal gas equation, PM equals dRT. So yeah, we'll skip that one. Let's take a look at this other set. Okay. 35, how many grams of gas are present in each of the following cases? So we've got 0.1 liters of CO2 at 307 torrs and 26 Celsius. 35 is very similar to 33, it looks like. So you've got volume, pressure, and temperature. Yeah, all three cases give you volume, temperature, and pressure. So once you've got your volume, temperature, and pressure, just plug those into the ideal gas equation and you should get your number of moles, and then multiply that number of moles by the molar mass and you can get your grams. You will need to do some conversion, of course, or change the version of the ideal gas constant that you use depending on the pressure and volume units. So for example, part A, they give you liters for volume and torrs for pressure. So I would use 62.36 liter torrs per mole Kelvin for my ideal gas constant. Either that or continue using 0.08206, but make sure to convert your torrs to atmospheres first. And of course, always convert your temperatures to Kelvin. Part B looks like you've got liters in kilopascals. So again, you need to convert the kilopascals to atmospheres or torrs, depending on which version of the gas constant you plan to use. And part C, you need to convert milliliters to liters, and torrs, you can either continue using them as long as you use the appropriate version of the gas constant, or you can convert the torrs to atmospheres. But yeah, 35 otherwise is pretty similar to 33. Use the ideal gas equation to get the moles, and then use the molar mass to get the grams. 36. A high altitude balloon is filled with a bunch of hydrogen at a temperature of 21 Celsius and pressure of 745 torrs. What is the volume of the balloon at a height of 20 kilometers where temperature is lower and the pressure is also lower? Okay, so for that you would just use the combined gas equation, assume the number of moles of gas is the same, and calculate, I guess, V2 in this case. You've got V1, P1, and T1, and you've got P2 and T2, and you need to calculate V2. Okay, we've done stuff like that, so we'll skip. 37. A cylinder of medical oxygen has a volume of 35.4 liters and contains oxygen at a pressure of 151 and a temperature of 25. What volume of oxygen does this correspond to at normal body conditions, that is 1 atmosphere and 37 degrees Celsius? Okay, similar to 36, so we'll skip. We've already done plenty of examples of that. 38. Pressure is given in bars, but we know how to convert it to atmospheres or whatever. Tank is filled at 20 and contains enough air to supply 1860 liters of air to a diver at 2.37 atmospheres. Was the tank filled to capacity at 20 degrees Celsius? This one might be interesting. Okay, let's take a look at 38. Let's have a look at number 38. So we've got the volume of the tank is 18 liters, and it's rated for a pressure of 220 bars. So 18 liters at 220 bars, that's maximum capacity. So that's max capacity. The real challenge with this problem is understanding what the problem is even asking for. But isn't that the case with all word problems? It's not always going to be cut and dried. Let's see, what else does it say? So the tank is filled at 20 degrees Celsius and contains enough air to supply 1860 liters to a diver at a pressure of 2.37. So I guess I'll call that T1, V1, and P1. So T1 is equal to, let's see, 20 degrees Celsius. So that would be, if I add 273, that would become 293 in kelvins. P1, they have it at a pressure of 2.37 atmospheres. So that's at the depth that the diver is swimming or diving. And that produces 1860 liters of air. I probably should have called these T1, T2, P2, and V2, but it's whatever. 1860 liters. Okay. Was the tank filled to capacity at 20 degrees Celsius? So I guess the temperature is constant, so that helps. So they filled the tank at 20 degrees Celsius, and I guess it can be assumed, so 20 Celsius or 293 kelvins. So it can be assumed that the pressure at that depth what am I even saying? The temperature, not the pressure, the temperature at that depth, we can assume it's the same. So yeah, temperature is not going to be a factor here. Otherwise, they would have told us the other temperature under the ocean. So it must still be 20 Celsius. What else do they say here? Well, I guess that's everything. So I guess there's two different ways we can go about this. We can either assume a volume of 18 liters and calculate the pressure, or we can assume a pressure of 220 bars and calculate the volume that it would occupy. And either way, we'd be able to tell whether or not the tank was filled to maximum capacity, whether or not you squeezed in as much gas into the tank as possible. I guess it would be more reasonable to assume that the volume when the tank is filled is just the volume of the tank itself, because a gas will just spread out to fill whatever volume it finds itself in. So they pumped in 18 liters worth of gas, because no matter how much gas you put in, if the volume of the container is 18 liters, then the volume of the gas in the container expands or compresses to 18 liters. So then, how much pressure did we squeeze in there? Was it 220 bars or was it less? Okay, so I'm going to go ahead and use, I guess we can use just Boyle's law here. P1V1 equals P2V2. Temperature is not a factor, and the number of moles of gas shouldn't be a factor either. They didn't bring it up at all. So let's see, we've got I could have done a better job organizing this information. 2.37 times 1860, so 2.37 atmospheres times 1860 liters equals P2 times 18 liters. Okay, the liters cancel out, so that's the units of liters gone. The units of pressure I get for P2 are going to be in atmospheres, and I'm going to then need to convert that to bars. So 2.37 times 1860 is going to be 4410 if I round to 3 sig figs. Equals P2 times 18, divide by 18, and if I round that to 2 sig figs, then that's going to be 240. So P2 equals 240 atmospheres. How much is that in bars? Let's see, so I guess I'll write it down here. 240 ATM. Can you guys see that? Yes. Okay. So 240 ATM, if we know that 1 ATM is equal to 1.013 times 10 to the 5? No, because the 10 to the 5 is already accounted for, because a bar is 10 to the 5 pascals. Okay. So, actually, it looks like it was filled beyond capacity. Did I do something wrong here? I feel like I've done something wrong, but no, an atmosphere is more than a bar. So, in fact, it's over capacity. I must have done something wrong. Let me look at it again. Maybe there was something in the figure that the problem refers to that I'm missing. I probably should have looked up the figure ahead of time. I didn't think it would matter when I did a quick read of this problem, but it does refer to figure 9.16. So I don't know if that has some missing data that we might need. Maybe it gives you like the temperature underwater. But yeah, I guess this problem is a bust because the result we got doesn't make sense. Oh well. Let's take a look at the next one. Next one says we've got a 20-liter cylinder with 11.34 kilograms of butane. It was opened to the atmosphere. In other words, its pressure should be equal to the atmospheric pressure. I'll assume it's at sea level unless they tell us otherwise. Calculate the mass of the gas remaining in the cylinder if it were opened and the gas escaped until the pressure in the cylinder was equal to the atmospheric pressure, 0.983. Well, there goes my assumption. And a temperature of 27 Celsius. Okay, so for this one, it doesn't look like it's going to involve any stoichiometry. We just have the mass of butane, which we would have to convert to moles, and once we've got our moles, let's see, we've got initial volume in moles. The volume is going to stay the same because it's the same container, so volume's going to be constant. Number of moles will change. They want the final number of moles if it were opened and the gas escaped until the pressure in the cylinder was equal to the atmospheric pressure and a temperature of 27 Celsius. So I'd assume that temperature is constant if the gas is just leaking out. I don't see why the temperature would have to change at all. Okay, let's give this one a try. I'm going to have to figure this one out as I go. I don't even remember why I included it, but it does look challenging enough that it's worth an attempt. So let's see. We have a 20-liter cylinder. Maybe I should draw it and get a visual on it. So we've got a 20-liter cylinder, and it's full of butane initially. It's full of 11.34 kilograms of butane, to be specific. So it's got 11.34 kilograms, and some of the butane just, you know, leaks out into the atmosphere. Okay. Calculate the mass of the gas remaining in the cylinder if it were opened and the gas escaped. Okay, so not a leak, but like they opened the lid. It was opened to the atmosphere. Calculate the mass of the gas remaining in the cylinder if it were opened and the gas escaped until the pressure in the cylinder was equal to the atmospheric pressure and a temperature of 27 Celsius. Okay, so I guess I'm overthinking this one. I'm overthinking it. Just use the ideal gas equation. Just use the ideal gas equation. PV equals nRT. The volume is fixed. So let's see. Pressure would be 0.983 ATMs. Volume would be 20 liters. Number of moles we can solve for. Ideal gas constant 0.08206 liter atmospheres per mole Kelvin. And then temperature was given as 27 Celsius. If I add 273, that's 300 Kelvin. Okay. Yeah, and then you can solve for the number of moles remaining, and from the number of moles remaining, multiply by the molar mass of butane, which you will get in grams. And I guess that's all they want. Yeah, you can convert it to kilograms if it turns out to be a high enough number where using kilograms would be more appropriate, but that's all you need to do. So solve for the number of moles and calculate the molar mass of C4H10 from your periodic table and get the grams, and that's it. The 11.34 kilograms doesn't even mean anything. It's a red herring. I thought they would have asked us to do something like calculate how much butane was lost, in which case, you know, you'd subtract it from the original amount, but yeah, we didn't need this 11.34 number. Now I'm wondering, looking back on 38, if I was overthinking that one as well. Let me reread 38 real quick and just double check. Maybe that might have been the thing I was overlooking. Pressure, volume, and temperature are given. And from that, we could get the number of moles, I suppose. No, there's definitely something missing. I'm sure of it. I'm missing some piece of data, and rather than scramble to look it up in the book, I'm just going to move on. Let me see, what do we have next? Oh, more use of the density form. Okay. So 48 here says, what is the density of laughing gas, dinitrogen monoxide, at a temperature of 325 kelvins and a pressure of 113.0 kilopascals? So for that, you would just use PM equals DRT. Nothing too fancy there. Same thing for 49, it looks like. And then 50 is a conceptual question. So let's do 48. And then we'll skip over to 50. So let's do 48 real quick, or at least the setup of 48. So we've got the density form of the ideal gas equation, pressure times molar mass equals density times gas constant times temperature. If I have dinitrogen monoxide at a temperature of 325 kelvins, so let's get, and a pressure of 113 kilopascals. Let's convert that. So 113.0 kilopascals is 113.0 times 10 to the 3. pascals, and I'm going to go ahead and convert that to atmospheres. So every 1.013 times 10 to the 5 pascals is equal to 1 atmosphere. And if I do that, divide by 1.013 times 10 to the 5, that's going to give me, if I round to 4 sig figs, 1.115. 1.115 atmospheres. Okay. And temperature is given as 325 kelvins. The other thing I need to calculate is the molar mass of dinitrogen monoxide. So 2 nitrogens give us a total of 28.014. I think we did that earlier somewhere. I'm pretty sure we did that somewhere up here, but maybe I'm mistaken. I could have sworn. Oh, yeah, there it is. Yeah, 28.014 for the 2 nitrogens, and then add the oxygen. So 28.014 plus 1 oxygen, which is 15.999, gives me 44.013 for the molar mass. 44.013 grams per mole. Whoops, not grams per milliliter, grams per mole for dinitrogen monoxide. Let's see, so that's pressure, that's molar mass. Temperature is already in kelvins, so we're good to go. So 1.115 in atmospheres times 44.013 in grams per mole equals density times 0.08206 in liter atmospheres per mole Kelvin. Writing it down here so that I don't run out of space, times temperature 325 kelvins. Okay. And again, unit check. Kelvins cancel with kelvins there. Moles in this denominator cancel with moles in the denominator of the other side of the equation. Atmospheres in the numerator with atmospheres in the numerator. And that leaves grams in the numerator. And then once I divide this over to the left-hand side, it'll be liters in the denominator. So density comes out in grams per liter. Okay. Let's take a look. So I guess I might as well crunch the numbers while I'm here. So 1.115 times 44.013 is 49.07. 49.07 divided by 0.08206 is 597.977, so I guess 598.0. And then divide 598.0 by 325, and that's 1.84. So the density is 1.84 grams per liter. Okay. 49 is pretty much the same thing, but you're doing it for free on 12, then you don't need to do a conversion because the pressure is already in atmospheres. You do need to convert the temperature, but that's easy enough. Number 50 says, which is denser at the same temperature and pressure? Dry air or air saturated with water vapor? Explain. So the answer, of course, would be air saturated with water vapor, because air saturated with water vapor, well, it has more gases in it, right? It's got more gases in it. It's got all the gases that dry air has, the oxygen, the nitrogen, and all the other atmospheric gases, plus the water vapor. It's just like Dalton's law of partial pressures, the example that I gave for that. Where was it? Wait, no, it's past this. There we go. Yeah, if I add water vapor to dry air, but I don't change the size of the container, and in our case, I guess the container is just the Earth's atmosphere, so you're not changing the size of that anytime soon. If there's more water vapor in there, then there's more particles of gas, which would raise the pressure. It would raise the total pressure, and if you raise the total pressure, well, then you raise the density, because just look at the density form of the ideal gas equation. If anything on the left-hand side goes up, then the density should also go up. Or I guess if you solve it for density, density is pressure times molar mass over the gas constant times the temperature. So yeah, the higher the pressure or the molar mass, the greater the density. More gases means more partial pressures contributing to the total pressure, means more density. I think I may have said those words out of order, and when I review this video, I'm probably going to have to call myself out on saying something silly. Or maybe my short-term memory is just failing me, and I said something that was perfectly fine. Who knows? Let's see. Where do we want to go from here? I guess now, finally, some problems that actually do involve stoichiometry. Woohoo! Let's see. We've got 51 is a cylinder of oxygen gas used in breathing by patients with emphysema. Has a volume of 3 liters at a pressure of 10 atmospheres. If the temperature of the cylinder is 28 Celsius, what mass of oxygen is in the cylinder? I suppose you could solve this using the density form of the ideal gas equation. But let's try and... But is it worth it? I'm thinking no. Okay. Let's skip 51. What about 52? So it gives us... It's asking for molar mass. They give us mass and volume. Okay, you can solve that with the density form of the ideal gas equation. We've seen that. 53, same business. 54. Oh, 54 is kind of interesting. So 54 says, how could you show experimentally that the molecular formula of propene is C3H6 and not CH2? So this goes back to something we learned about in, what was it, part 2 or was it part 3, where we talked about empirical formulas. Empirical versus molecular formulas. Let's talk about this for a second. So, empirical versus molecular formulas. So, of course, C3H6 is the molecular formula, and the empirical formula that you get for it is CH2. So if you took propene and did a combustion analysis for it, you would get CH2 as your empirical formula. You would find that the ratio of hydrogen atoms to carbon atoms is 2 to 1. But that wouldn't be enough information to determine that it's C3H6. So to determine what the molecular formula is, you need the molar mass. One way to get the molar mass is to use mass spectrometry, is to use the mass spectrometer, which we did explain in whichever video it was where we covered that. I think it might have been part 3, but my memory is a bit hazy. So instead of using a mass spectrometer, you could also calculate the molar mass for a gas by simply measuring its pressure and volume and temperature and mass. So if you measure the pressure, volume, temperature, and mass, you can get the molar mass by using the density form of the ideal gas equation. Pm equals dRT, or more specifically, M equals dRT over P. So to get the density, you'd need to calculate the mass and volume. Shouldn't be too hard to do. So the way I would do it if I wanted to design an experiment for this is I would have some sort of rigid container, make sure to vacuum all of the air out of it at first, and let's see, so have a rigid container so that its volume can't change, vacuum all the air out of it, and then when it's completely vacuumed out and emptied and sealed, I would weigh the container. Then I would perform an experiment that would pump in a given amount of propene gas, maybe just inject it directly if I have it ready-made, and then go back and weigh it again with the propene gas inside of it, and whatever the increase in the mass of that container, that must be the mass of the gas that I pumped into it. So that's how I would get the mass of the gas, and because I know the volume of the container, I can just take the mass over the volume, and there's my density, and use a pressure gauge to measure the pressure and a thermometer to measure the temperature, and yeah, you'd be good to go. You'd have all the data you need to calculate the molar mass. Okay, so that was an interesting conceptual question. Experimental design is something that you're going to want to know, especially if you're taking AP chemistry. They do have some experimental design questions on the free response portion sometimes. 55. We have density at STP, calculate the molar mass. Yeah, we'll skip. 56. What is the molecular formula of a compound that contains 39% carbon, 45% nitrogen, 16% hydrogen, if 0.157 grams of the compound occupies 125 milliliters with a pressure of 99.5 kilopascals at 22 Celsius? Okay, so I'll outline the steps, but as for the actual number crunching, I think we'll skip that part. Let's go ahead and do this one. Let's get a new sheet out here. So we have 39% carbon, and 45% nitrogen, and 16% hydrogen. Okay, from this we can get the empirical formula at the very least. I'm going to make a guess and say it's going to be CnH2, but let's see whether or not that guess is even close to being right. So how do we find empirical formulas if we're given mass percents? I hope you remember. If we're looking for ratios, it doesn't matter what the actual amount is, so let's just assume we have 100 grams. If we assume we have 100 grams, then it makes it easy to calculate the moles of carbon, nitrogen, and hydrogen, because it makes it easy to get the grams of each of them. Assume 100 grams for your sample. That would mean we've got 39 grams of carbon, 45 grams of nitrogen, and 16 grams of hydrogen. Okay. Then convert your grams of carbon to moles. You should be able to kind of do that without writing out the dimensional analysis steps at this point. 39 divided by 12.011 is 3.25. Yeah, I'll keep some extra decimal places here. Let's do 3.247 just to be on the safe side. I'm neglecting the sig fig rules because, well, you don't really need to round to an appropriate number of sig figs. You need to round to whole numbers in the end, so you can bend the rules a little bit. You may remember that that ended up hurting me in the end when I did a combustion analysis problem, but that's in the past. Let's see, 45 divided by 14.007 is going to be, let's take 3.213. I'm feeling tempted to round to 2 sig figs, but I'll carry on. And then for hydrogen, 16 divided by 1.008 is 15.873. Well, I know it's not going to be CnH2, but let's divide by the smallest. So 3.247 over 3.213 gives me 1.011. That'll give me 1, and then 15.873 divided by 3.213 is 4.940. Okay, so essentially 1 to 1 to 5, it looks like. So the empirical formula would be CnH5. Okay, let's get the empirical mass. Not an official term, but that's what I like to call it. Empirical mass. So 12.011 for carbon, plus 14.007 for nitrogen, plus 5 times 1.008 for hydrogen, 31.058. 31.058 grams per mole. So that's the molar mass of the empirical formula. Now let's take a look at what the actual molecular mass is. Let's take a look at the molar mass of the full compound. So going back to the data that they gave us here, we have mass is 0.157, volume is 125 milliliters, pressure is 99.5 kilopascals, and temperature is 22 Celsius. Okay. So I'm going to write all that stuff down. So we have 0.157 grams for the mass. For the volume, I'm going to convert it to liters, so it's going to be 0.125 liters. I expect you to be able to do that conversion in your head. You're just moving the decimal 3 places. Then we've got, let's see, pressure is 99.5 kilopascals. That's 99.5 times 10 to the 3 pascals. I'm going to convert that to atmospheres. So every 1.013 times 10 to the 5 pascals is equal to 1 atmosphere. And yeah, that'll give us the pressure in atmospheres. And then the temperature, they gave us 22 Celsius. If I add 273, that becomes 295 Kelvin. And now to calculate molar mass. So let's see, pressure times molar mass. I'm going to divide the pressure over to the other side. So pressure times molar mass equals density, gas constant, temperature. Divide both sides by the pressure, and that moves the pressure down to there. Okay. Density is the mass in grams over the volume in liters, and then our pressure is in atmospheres. So volume in liters, pressure in atmospheres, gas constant is what we're used to, 0.08206. And I think I'm gonna skip on writing out the units this time. I think we've seen enough examples to demonstrate that we will get units of grams per mole. So let's see, 0.157 over 0.125 to get the density is 1.26 if I round to 3 sig figs. So 1.26 times 0.08206 times 295 over, well, I haven't converted the pressure yet, so let's do that. 99.5 times 10 to the 3 divided by 1.013 times 10 to the 5 is 0.982. So that's 0.982 ATMs, and that's what I'll plug in for the pressure here. Okay, and I said I was going to skip on writing the units. So I'm just going to do it all in one go rather than round to the appropriate number of sig figs at each step, because this is an empirical formulas problem. I think I can get away with it. 1.26 times 0.08206 times 295 over 0.982 all in one go is 31.06 roughly. Approximately 31.06. Oh, which is pretty much exactly equal to 1 times the empirical mass. So in this case, the empirical formula and the molecular formula are the same. The molecular formula is 1 times the empirical formula, CnH5. What would the structure of this thing be? Let me try and guess what it would look like. We're going to be doing Lewis structures pretty soon. Let's see, so I'd probably have carbon as a central atom. 3 hydrogens. Okay, yeah, this wasn't as complicated as I thought it would be. Okay, yeah, there it is. Methylamine. You'll learn how to do this soon enough. It's coming in due time. Actually, how many videos from now will we cover Lewis structures? Based on what I have set up, next time is going to be thermochemistry, then we're going to talk about electronic structure, then Lewis symbols. So it looks like what I'm recording right now I think is part 5, so it looks like part 8 is when we will learn how to draw these. So it's coming soon. We're almost there. Okay, and I guess that problem is done. So let's take a look at, maybe these will actually involve some stoichiometry. I was pretty sure after going through them, because that's how I labeled them, but maybe I just didn't notice that you could use the ideal gas equation in its density form to skip most of the hard parts. 57. We've got a cylinder of gas for calibrating blood gas analyzers. Okay, so for 57, all you would have to do is convert the grams of each gas to moles using their molar masses. And once you know the moles of each gas, you can calculate the total moles of gas, and whatever total moles of gas you have, you can plug that into the ideal gas equation and you should be good to go. I think we're better off doing this one just to be on the safe side. Or at least the setup of it. Okay. So we've got a volume of 36 liters. Pressure is what we need to calculate. Number of moles will be moles of each gas added. So let's see, we've got carbon dioxide, oxygen, and nitrogen. Whoops. Nitrogen and oxygen. We'll calculate each of those individually later. Temperature is 25 Celsius or 298 kelvins. And yeah, we've got the individual masses of each of the gases. So to calculate pressure, we've got 350 grams of carbon dioxide. So carbon dioxide has a molar mass of 12.011 plus 2 times oxygen, 2 times 15.999 is 44.009. If I take the grams of carbon dioxide, 350 divided by the molar mass of carbon dioxide, rounded to 3 sig figs, that's 7.95 moles. Okay, nitrogen gas, so we have 4,880 grams of nitrogen, 4880, divided by the molar mass, which was 28.014 grams per mole. Rounded to 3 sig figs, that's going to be 174. 174 moles of nitrogen gas. Not a surprise given how much nitrogen gas we had in grams. And then we've got 805 grams of oxygen. So 805 divided by the molar mass of oxygen is, let's see, 15.999 times 2 is 31.998. So 805, was it? Yeah, 805 divided by 31.998 gives me 25.2 moles of oxygen. And yeah, for addition and subtraction, we go with least decimals. The nitrogen moles have no decimals, so we round to no decimals. So 7.95 plus 174 plus 25.2 rounded to no decimals gives us a total of 207 moles of gas. Okay, 207 moles of gas. We can plug that into our ideal gas equation, and the rest is history. So PV equals nRT. I'm going to divide by V on both sides. So P equals nRT over V. And yeah, just plug the numbers in. So we've got 207 times 0.08206. That'll give us the pressure in atmospheres, times 298. And of course, we're going to need our volume to be in liters, which it is, 36.0. And there we go. So step by step, 207 times 0.08206 gives us, I guess that would round to 17.0. 17.0 times 298, 5,066, which I guess I'd round to 5,070. 5,070 divided by 36.0 would round to 141 atmospheres. Yeah, if I use liters, I should get atmospheres as long as I use liter atmospheres per mole Kelvin as my ideal gas constant units, which I did. Okay, that solves that problem. Any other interesting ones here? 58. Okay, 58 is rather interesting. So let's see, it says a cylinder of a gas mixture used for calibration of blood gas analyzers in medical labs contains 5% carbon dioxide, 12% oxygen, and the remainder nitrogen at a total pressure of 146 atmospheres. What is the partial pressure of each component of this gas? So to get the partial pressures, I need to figure out the mole fractions. To get the partial pressures, I need the mole fractions. And to get the mole fractions, I need the moles. Or at least the ratios of the moles. So they gave us the percents, and that's not percent moles, that's percent mass, right? Whenever you see anything given in percents, assume it's percent mass unless they say otherwise. So working with the assumption that those are percent masses that we are given, we have a mixture that is 5% CO2, 12% oxygen, and the rest is nitrogen. So the rest would be, let's see, that's 17 already, so that means 83.0% would be nitrogen gas. Assume 100 grams. Assume 100 grams total. Assume 100 grams for your whole sample. And what would that give us? So that would give us 5 grams of carbon dioxide, 12 grams of oxygen, 83 grams of nitrogen. So 5 grams carbon dioxide, 5.0 divided by the molar mass of carbon dioxide, which was, I still have it stored in my calculator somewhere, 44.009. That's going to give us 0.11, so 0.11 moles. Then for oxygen, so that's going to be 12.0 grams divided by molar mass of oxygen is 31.998, gives us 0.375 moles of oxygen gas. And then for nitrogen gas, 83.0 grams divided by 28.014 grams per mole is 2.96 moles of nitrogen gas. Pretty interesting how nitrogen ends up being the majority of the gas in both this problem and the previous problem. It's almost like they took a bunch of air from the atmosphere, where almost 80% of it is nitrogen, and they just pumped in or pumped out some of the gases they wanted or didn't want. Anyway, let me see. So now we've got the moles, we can calculate the mole fractions. And once we've got the mole fractions, we can calculate the partial pressures. So mole fraction of carbon dioxide is going to be 0.11, the moles of carbon dioxide over the moles of everything. Let's go ahead and add these. So 0.11 plus 0.375 plus 2.96 is 3.445, but according to decimal rules, I'm going to have to round that to 2 decimal places, so 3.45. So N total is going to be 3.45 moles. So 0.11 over 3.45 for the mole fraction of carbon dioxide. Mole fraction of oxygen gas is going to be 0.375 over 3.45, and the rest is going to be nitrogen. Let me work these out first to see how much space I'm going to have. So 0.11 over 3.45 is going to be 0.032. And then 0.375 over 3.45 is 0.109. 0.109. And there are no units for the mole fraction, by the way. I forgot to mention that earlier. Since you're dividing moles by moles, there shouldn't be any units. The units cancel out. So mole fractions are unitless. Anyway, mole fraction of nitrogen is 2.96 over 3.45 equals 2.96 over 3.45, 3 sig figs, that would be 0.858. 0.858. Yeah, you should never have a mole fraction greater than 1, and if your mole fraction is equal to 1, it better be because it's the only gas in the mixture, in which case it wouldn't really be a mixture. So yeah, if I were to double check these, they should add up to 1 or approximately 1. It'll almost never be perfect, but a quick check you can do is add those numbers. I'm going to do that real quick. 0.032 plus 0.858 plus 0.109 adds up to 0.999, so that's essentially 1. So yeah, they should add up to approximately 1. Okay, So now we've got the mole fractions, we can get the partial pressures very easily. I'm just going to do one of them and leave the rest up to you. So let's do, I don't know, the partial pressure of oxygen. Partial pressure of oxygen equals mole fraction of oxygen times total pressure. So that would be 0.109 times the total pressure. The problem told us that the total pressure is 146 atmospheres. So 0.109 times 146 is 15.9. 15.9 atmospheres of pressure exerted by just the oxygen in the mixture, and you can follow similar steps to get the partial pressures of carbon dioxide and nitrogen gas. Okay, let's take a look at another one. 59 says we've got a sample of gas isolated from unrefined petroleum. What's the partial pressure of each component? We already did that, so I'll skip 59. 60, we've got a mixture in a closed container at STP. Find the volume of the container, assuming that the gases exhibit ideal behavior. Okay, so 60, you just want to use the molar volume at STP and calculate the moles of each gas that are present. Okay, let's do that one. So we have 0.200 grams hydrogen, 1 gram of nitrogen, and 0.820 grams of argon, which is a noble gas. Not that knowing that is particularly relevant to this problem, but being able to recognize noble gases is a good skill to develop. It's advantageous. Let's see, what else do they tell us? It's at STP, and they want the total volume of the gases. Okay, so converting to moles, I'm gonna do hydrogen divided by its molar mass. So let's see, that would be 2 times 1.008, so 2.016. So 0.200 divided by 2.016 to 3 sig figs, that's 0.0992. 0.0992 moles. For nitrogen, divide by, let's see, that would be 28.014, 0.0357, 0.0357 moles. And then for argon, I'm just going to look that up from my periodic table real quick. Argon is 39.948. 39.948. So 0.820 divided by 39.948 gives me 0.0205 moles. 0.0205 moles. Okay, so we got the moles of each of the individual gases. Then what does it tell us to do? Find the volume of the container, assuming that the gases exhibit ideal behavior and assuming that it's at STP. So, of course, the volume of the container should equal the total volume of all the gases in the container. So, let's see, total moles. Let's get our total moles, which would be 0.0992 plus 0.0357 plus 0.0205. And that's going to be, yeah, we did addition, so we don't round to 3 sig figs. We keep it at 4 decimal places. So 0.1554 is your total moles. 0.1554 moles. And then, of course, the molar volume at STP is 22.4 liters per mole. So we can say 0.1554 moles of gas times 22.4 liters for every 1 mole of gas gives us a total volume of, rounding to 3 sig figs, 3.48 liters. So if the gases exist in a mixture, their volumes in that mixture are equal. The volume of the mixture is equal to the volume of each gas in the mixture. Something to be really, really careful about. 3.48 liters is the volume of the hydrogen and the volume of the nitrogen and the volume of the argon. All 3 gases will spread out evenly throughout the entire container. They take up the entire volume, so be careful not to make the mistaken assumption that the volumes of the gases are additive. They are not. If you mix 2 gases in a container, they don't, take up different parts of the container. There's plenty of empty space around the gas particles where they can just spread out through the whole container and take up the maximum volume. The volume of a gas equals the volume of its container. Always, always, always. So, although you probably would have still gotten a correct answer if you just took each of these and multiplied them by 22.4 individually and then added the results, although you'd end up with the same result, the logic behind it would have been incorrect. So if I did 0.0992 times 22.4 plus 0.0357 times 22.4 plus 0.0205 times 22.4, I would not be getting the individual volumes of these gases. In fact, I'd be getting something that's kind of meaningless as far as chemistry is concerned. Anyway, let's carry on and look at another one. Are there any other interesting problems here that we need to go over? Let's see, so we just finished 60. What does 61 say? Most mixtures of hydrogen gas with oxygen gas are explosive. However, a mixture that contains less than 3% oxygen is not. If enough oxygen is added to a cylinder of hydrogen at 33.2 atmospheres to bring the total pressure to 34.5 atmospheres, is the mixture explosive? Okay, so 61 should be pretty quick if you know what you're doing, which I don't expect if you're learning this for the first time, but that's what you should aspire to by the end of your school year or the end of your course. So they said 3% oxygen. So I guess 3% oxygen by mass. If it's less than 3% oxygen by mass, it's not explosive. So they told us we have a cylinder of H2. So the pressure, the partial pressure of H2 was 33.2 atm. Okay. And the total pressure went up to 34.5, which means the extra 1.3 atmospheres worth of pressure must be due to the oxygen. Pressure of oxygen plus pressure of hydrogen equals the total pressure. That's Dalton's law of partial pressures again. So the pressure of oxygen plus 33.2 equals 34.5. Some of you don't need me to write this out, but just in case, I want to show the reasoning. So that would leave us with, 1.3 atmospheres would be the partial pressure of oxygen. Okay. So something I didn't mention before when talking about mole fractions is that there's another way you can calculate the mole fraction of a gas. Since the proportions between moles of gases and their partial pressures are the same, you can actually use the ratio of the partial pressure to the total pressure to figure out the moles of a particular gas compared to the total moles of gas, which is something we're going to need here because we don't know the total moles of gas. If we go back to something I wrote earlier, I remember writing that partial pressure of an individual gas over the number of moles of that individual gas is equal to the total pressure of all the gases over the total moles of all the gases. Well, if you rearrange this equation, so if I multiply by n sub a and divide by p sub t, so let's multiply first, so we get p sub a equals p sub t times n sub a over n sub t, and then divide by the total pressure, so we get P of A over P total equals moles of A over moles total. And there you go. So moles of a particular gas over the total moles of gas, which is the mole fraction of gas A, is also equal to the partial pressure of that gas divided by the total pressure. And since we don't know the numbers of moles, we can't use moles of oxygen over total moles. We don't know the total moles of hydrogen and oxygen, so we have to use the partial pressures. And if we do that, then what we get is... Oh, I just realized this one isn't going to be as quick as I thought it would be. There's a little bit more to this after the step I'm about to carry out. So we've got 1.3 as the partial pressure of oxygen over the total pressure of 34.5 equals 1.3 over 34.5 is going to be 0.038. 0.038. Okay, so that's the mole fraction of oxygen, but that's not the percent oxygen by mass. To get the percent oxygen by mass, I'm going to need to make an assumption. So first let's calculate the mole fraction of hydrogen, which shouldn't be too hard to do. I'm just going to do 1 minus 0.038, which leaves us with 0.038 0.962 is the mole fraction of hydrogen. That way total should add up to 1. Okay, so now I've got the mole fractions of both, and I need to make an assumption about the amounts of hydrogen and oxygen I have so that I can calculate the percent oxygen by mass. Let's do that on another page, or maybe I can squeeze that in up here. No, I'll do it on another page. So I'm going to copy these two bits of information here. So we've got mole fraction of oxygen is 0.038, and mole fraction of hydrogen is 0.962. And here's what I'm going to do. I'm going to assume 100 moles total. I'm going to assume that the total moles of gas is 100. Or in fact, I'll make it 1,000. That would make this even easier. I'm going to assume 1,000 total moles of gas. If the total moles of gas are 1,000, and the proportion of oxygen in there is 0.038, then that means I have 38 moles of oxygen over 1,000 moles total. So this would give us, based on our assumption, 38 moles of oxygen and 962 moles of hydrogen. Okay, convert those to grams. 38 moles of oxygen, 38 times 31.998 is 1215. I guess I would round that to just 1,200 grams. 1,200 grams of oxygen. And then for hydrogen, 962 times molar mass of hydrogen gas is 2.016, and that's going to be 1940, it looks like. 1940 grams of hydrogen gas. And if we go ahead and calculate the percent oxygen by mass, then this would tell us percent oxygen gas by mass is the mass of oxygen, 1,200 grams, over the total mass, 1,200 plus 1940, times 100%. And I think you can already tell that's going to be way more than 3. 1,200 over the sum of 1,200 and 1940 is 38%. So we're looking at 38%, way more than 3%. This mixture is explosive because there's enough oxygen in there to cause an explosion, at least according to the problem itself. So yeah, it would have been very easy to look at the mole fraction and assume this means that you've got 3.8% oxygen, and I guess you would have reached the correct conclusion, but you would have gone about it the wrong way. And, you know, reaching the correct conclusion incorrectly is going to come back to bite you someday, because if you don't learn how to reach it correctly, one day you might encounter a problem that that would be misleading if you solved it incorrectly. You get what I'm trying to say. Is there anything else I wanted to say about this problem before moving on? I don't think so. Let's see. Is there anything else left on this list? that's worth going over. So we just did 61. 62 says we've got mercury vapor analyzer, can detect concentrations of mercury atoms in the air down to, it looks like 2 times 10 to the negative 6 milligrams per liter, or 2 nanograms per liter is what I would have written. At this concentration, what is the partial pressure of mercury gas if the atmospheric pressure is 733 torr at 26 Celsius? So yeah, for this you could just use the ideal gas equation pretty easily. I would probably use the density form, so convert the milligrams per liter to grams per liter and just go from there. I don't think we need to cover that one. Okay, then I think it's time to talk about collecting gas over water. I think it's time to talk about collecting gases over water. So let's take a look at the following apparatus. So earlier in this video we did mention something called vapor pressure, and now it's going to become even more important. We already saw how vapor pressure messes with your or can mess with your calculation of pressure using a barometer, but it can also mess with some stoichiometric calculations that you do in the lab. Sometimes in the lab you're going to do a reaction that, you know, creates gases, a gas forming reaction, some gas bubbles out of the mixture, and you can collect those gas bubbles, and sometimes you have to collect those gas bubbles over water. Well, if you do that, then you're also going to collect some water vapor molecules that are hovering over the surface of the water, because even though you can't see it, water is evaporating even when it's not boiling. Water is always evaporating, at least partly, and so there will be some traces of water vapor hovering above the surface of the water at any given time. It'll be freshly evaporated water that exists in amounts that might be too small for you to see with the naked eye, but they're still significant enough that they can affect your calculations. When you try to calculate how much of your gas you collected, you usually don't want to count the water vapor with that gas. So that's the problem that we deal with. But of course, as long as we know the vapor pressure of water at different temperatures, we can just subtract out the partial pressure of the water vapor, and that'll leave us with just the pressure of whatever gas we collected. And as long as you have other information like temperature, then you can calculate how much gas you ended up collecting. So let me show you this table of vapor pressures for water. This is something we're going to be using for a couple of problems, maybe one or two. But yeah, so this table, it lists the vapor pressures of, it looks like ice and water at different temperatures at sea level. So it's really just something you have to look up. You can't really calculate it through any formal equation, at least not any equations that I know of. But yeah, there it is. That's vapor pressure of water. I guess we should probably talk about how vapor pressure is determined and where it gets its name from, because that's not entirely clear cut. So let me flip back to the camera real quick. Well, it probably won't be quick, but we'll see. We'll talk about vapor pressure again in a later chapter where it becomes more important. But let's take a look at the following example. Suppose I have a container full of water, let's say a beaker, for example. That's a very poorly drawn beaker. Maybe that makes it more believable. Let's say there's some water in it. And let's say that I have this beaker inside of a sealed container. Let's say I have this beaker inside of a sealed container. So any water vapor that comes off of this beaker will be stuck inside of this container. It won't be able to escape outside to the atmosphere. And I guess you could also claim that the gases, the water vapor in here, is protected from the atmospheric pressure. So, of course, the way evaporation works, if you're not at the boiling point, let's say for water, for example, is that you have water at, say, room temperature, and some of the water molecules are going to be moving rather slowly. Other water molecules might move faster, especially after having several collisions with other water molecules. So when they have all these collisions, some of them gain speed, some of them lose speed, and eventually some of those water particles gain enough speed that they just manage to escape the liquid state. So they just kind of jump out of the solution into the gas phase. Okay, and that's all fine and dandy, but as you get more and more water vapor particles here, as you get more and more of these gas particles, eventually these gas particles are moving about somewhat randomly as well, and some of them might come crashing back into the liquid state, and they might get captured by the liquid and, you know, reliquefy, if that's even a word I can use. So more gas particles means more chances for that vapor to collide with the surface of the water, or whatever the liquid is, and turn back into a liquid. Fewer gas particles means a lower likelihood of that happening, and a greater likelihood of, you know, liquid particles turning into gas instead. So you always have this going on in both directions at the same time, and once you reach the point where the number of particles escaping the liquid phase is being immediately compensated for by the amount of gas particles crashing back into the liquid, at that point, that's when you see the pressure inside this jar stops building up. So if I were to attach a pressure gauge to this bell jar container thing that's covering my beaker, at first I would see the pressure gradually going up, and eventually it would stop, and it would stop because there would no longer be an increase in the number of gas particles creating pressure inside the bell jar. Instead, the new gas particles being formed are being, I guess, canceled out by the old gas particles turning back into liquid. So once you reach that maximum pressure, that's what's called the vapor pressure. The amount of pressure that the vapor exerts, so vapor pressure is the amount of pressure that a vapor exerts, the pressure a vapor exerts on its liquid form when in equilibrium. And that term equilibrium is going to come up again in chemistry. Basically, equilibrium happens whenever two things are changing at the same time and the two changes are opposite, and they reach a point where both of the changes are happening at the same speed, at the same rate. So in this case, the two changes that are happening at the same rate, that'll eventually be happening at the same rate, is water vapor turning into liquid water and liquid water turning into water vapor. At first, water vapor turning into, water liquid turning into water vapor at first is happening much faster than water vapor turning back into liquid water, but as more and more water vapor particles are formed, there's a greater likelihood and therefore a greater rate of water vapor turning back into liquid water. So eventually those two rates start to counter each other, and they never actually stop. So evaporation never actually stops, nor does, I guess, condensation stop, but they do reach a point where they almost immediately undo each other, so you won't see any change in the bigger picture. But yeah, so that's the definition of vapor pressure. So you can also think of this as the point where the pressure that these gas particles exert downward on the surface of the liquid is kind of equal to the pressure that the surface of the liquid exerts upward against these gas particles. That idea will be important later when we talk about how vapor pressure changes based on the concentration of a solution. But I think at this point I've already told you more than you currently need to know about vapor pressure. So if this was all too much for you, don't worry too much about it. We will talk about it again later. I just feel like introducing it now will help for when you really need to understand it at a later time. Okay, so that's collecting gas over water and vapor pressure. Let's see where we want to go from here. So I want to look at some problems from here. We've got, which one should I do? So 63 says we've got carbon monoxide collected over water. Oh, I guess that's the only one, is it? Okay, I guess it's that one example. A sample of carbon monoxide was collected over water at a total pressure of 756 torr and a temperature of 18 degrees Celsius. What is the pressure of the carbon monoxide? All right, so we need to look up the vapor pressure of water at 18 degrees Celsius, which we can easily do. Let's switch to that real quick. So at 18 degrees Celsius, the vapor pressure of water is 15.5 torrs. 15.5 torrs. Okay. So we've got 15.5 torrs for the vapor pressure of water. Let me write that down. So that's going to be the partial pressure of water, pH2O. And we've got a total of 756 torrs. What's the partial pressure of carbon monoxide? Okay, so P total, 756 torrs. Pretty simple and straightforward. All you have to do is subtract, because pressure of carbon monoxide plus pressure of water vapor equals the total pressure, assuming there's nothing else mixed in with those two gases. So 756 minus 15.5 is 740.5, or I guess 741 in keeping with our rules. So 741 would be the pressure of carbon monoxide, 741 torrs, and that's the end of that problem. They didn't ask for more, but usually when you get this type of problem, you'll be given the temperature at which the gas was collected, and also the volume that the gas took up in the container in which you collected it. And from there you can calculate the numbers of moles of gas collected, and usually that'll be followed up with some sort of stoichiometric calculation. So, you know, all stuff that you've seen before, all stuff that you know how to do, but the essential part is just subtracting out the water anytime you collect a gas over water. What do these other problems say? So 64 says, in an experiment in a general chemistry lab, a student collected a sample of a gas over water. The volume of the gas was 265 milliliters at a pressure of 753 torr and a temperature of 27 degrees Celsius. The mass of the gas was 0.472 grams. What was the molar mass of the gas? Let me see. So I guess in this case they already took that into account. They already subtracted out the partial pressure of the water, and they just gave you essentially the rest of the problem, like I was saying earlier. Should we go over it? We're given volume, pressure, and temperature, so we can plug that into the ideal gas equation to get moles or even density. Oh, yeah, and they gave you the grams. Okay, yeah, you can just use the density form of the ideal gas equation. We've seen this before. 65, anything interesting here? So it says, Joseph Presley first prepared pure oxygen by heating mercuric oxide, which is also known as mercury 2 oxide. Outline the steps necessary to answer the following question. Oh, finally, a good stoichiometry problem. We're doing this one. We're doing this one. Okay, so we have the balanced equation is given to us as 2HGO, and that's solid. Gives us liquid mercury plus oxygen gas. So it's asking what volume of oxygen gas is produced by the decomposition of 5.36 grams of mercury 2 oxide. So we've got 5.36 grams of this stuff, and we want to figure out how many liters of this stuff is formed, and it's not at STP, so we can't just use 22.4 for the molar volume. We're going to have to actually calculate the molar volume. Or we can calculate the moles and plug that into the ideal gas equation, whatever works for you. I guess that approach would probably be better here, but calculating the molar volume would be a better idea whenever you have to do it for multiple gases in the same problem under the same conditions. Anyway, let's go ahead and let me get the molar mass of mercury 1 oxide first. So mercury is 200.59, it looks like. So 200.59 plus molar mass of oxygen 15.999 gives me 216.589 grams per mole. 216.589 grams per mole. Okay. And we need to figure out the volume of oxygen gas formed. So I'm gonna start with 5.36 grams of mercury 2 oxide. And let's see, 5.36, we're going to need 216.589 here, grams, and that's 1 mole. And then for every 2 moles of HGO, we get 1 mole of O2. And that gives us moles of O2, and then we can stop there, or we can calculate the molar volume and add that as our next conversion factor. I think I'm going to do that this time. So every 1 mole of gas under these temperature and pressure conditions equals how many liters? That's something we can determine. I have some unused space over here, so let's make use of it. So let's see, I need to solve for the molar volume, which is the ratio of volume over number of moles. And that's just rearranging the ideal gas equation. So PV equals nRT. So divide the P over to here. The RT stays there, and the N got divided to there. Okay. So RT over P, what is it going to be? So 0.08206 is what I'm going to use, which means my pressure better be in atmospheres. Temperature is, what did they say? 23 Celsius. If I add 273, that becomes 296. 296 kelvins. And then for the pressure, they gave us 0.975 atmospheres. Glad they spared us from having to do conversions. I don't know why I wrote that in, but 0.08206 times 296. The spacing on this is kind of weird. Should have written the 2 closer to the 9. Gives me 24.3, and then 24.3 divided by 0.975 gives me 24.9. Gives me 24.9. I guess I'll write that here. 24.9 liters per mole would be the molar volume under these circumstances. So 24.9 liters of oxygen for every 1 mole. Again, alternatively, you could have stopped here, calculated the moles of oxygen, and then just used the ideal gas equation like normal. You're going to end up with the same result either way. So let's see. 5.36 over 216.589 is going to be 0.0247. And that's moles of mercury 2 oxide. And then divide that by 2, so 0.0247 over 2 is going to be 0.0124. And that's moles of oxygen gas. And then multiply that by 24.9, so 0.0124 times 24.9 gives us 0.00381 liters of oxygen gas. I think it would be more appropriate to convert this to milliliters, so move the decimal 3 places to the right. That gives you 3.81 milliliters of oxygen gas. There we go. That's the only stoichiometry problem that survived being shortcutted by the density form of the ideal gas equation. Okay, Let's see, what do I have lined up next for you guys? Let me see, what do I have lined up here? Okay, so I guess it's time to talk about kinetic molecular theory. I kind of hinted at it earlier when talking about vapor pressure. Okay, time to talk about kinetic molecular theory. So, these are the 5 postulates of kinetic molecular theory. And I'm just going to read them out loud. So, number 1. We assume, and this is, by the way, how we define ideal gases. So, these are the 5 things we assume. 1. Gases are composed of molecules that are in continuous motion, traveling in straight lines and changing direction only when they collide with other molecules or with the walls of a container. Second assumption. The molecules composing the gas are negligibly small compared to the distances between them. Number 3. The pressure exerted by a gas in a container results from collisions between the gas molecules and the container walls. Number 4. Gas molecules exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic, which is another way of saying they do not involve a loss of energy. You can learn more about collisions if you study physics. If you already know about conservation of momentum and all that stuff, then you might have a little bit of an advantage in understanding this. And then number 5, the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. So the higher the temperature, the higher the average kinetic energy. Average kinetic energy depends solely on temperature. Or I guess the reverse would also be true. Temperature solely depends on the average kinetic energy. So there are a lot of conceptual questions we can ask here, and I think I'm going to want to pull up some of them right now. Let me see. Oh, wait. Are those the right questions? I probably should have double-checked these before I started recording, but let me look through them real quick. Okay, yeah, I do think we're good to go with these problems. Why did I label it? Should I or should I not? I think I'll save it for later. Okay, let's look at these problems. So let's move over to here. So number 90 says, using the postulates of the kinetic molecular theory, explain why a gas uniformly fills a container of any shape. So this one is kind of a tough question, because the idea that a gas just fills out the entire shape of any container that it's, you know, stuffed inside of is so intuitive that you just feel tempted to answer this question with, well, it's just obvious. And that's not really a proper explanation. The hardest things to explain are the things that you never imagined you would need to explain. The things that feel so simple and intuitive that you never bothered thinking about an explanation for them. And that's what I really like about this problem. I don't even know if I can answer it that well, but I'm going to make an attempt. So let me switch over to the camera and let's talk about it. Why is it that gas particles evenly spread out? How is it that they spread out evenly throughout the volume of a container, no matter what the shape of the container is? So let's start with a very standard container, a box. And let's also draw some weirdly shaped container. Let's say, think. What kind of weird shaped container can I make? Let's say, well, it doesn't have to be too weirdly shaped. Let's draw an Erlenmeyer flask, and let's say that I have it plugged up. Yeah, I'll do that. Okay, those are two containers with two different shapes. Let's see what happens if I inject some gas into a container. So, if I put a gas in a container, if I inject some gas in there, then let's say it gets injected into this corner, for example. Let's say there's a place where you can, inject in some gas, and it just so happens to be in this bottom corner here. What's going to happen? Well, the gas particles aren't just going to stay here, and why are they not going to stay here? If they stayed here, then the distribution would definitely not be uniform, right? Because, you'd have a strong concentration of gas particles in one corner of the container and nothing in the rest of the container. So, of course, these gas particles, they're going to have to collide with each other. They're constantly moving around, and they're going to bump into each other, they're going to bump into the walls of the container, and because they do that, they end up spreading out. If these gas particles stay near each other, they're going to collide with each other more often, and if they collide with each other more often, what's going to happen? They're going to bounce away from each other. So eventually they have to get to a point where they scatter pretty much evenly, because if they're not scattered, then they'll be close enough to collide more often, which would then cause them to start scattering. This is what we call a proof by contradiction. Probably not what you came here to learn, but this is something from logic theory, proof by contradiction. You might have heard of this in your math class, because math isn't really about numbers, it's about logic. Numbers just happen to be very useful for doing logic experiments on. But yeah, this is what we call a proof by contradiction. If it's hard to prove why something is true, then prove that it would be impossible for it not to be true. That's called proof by contradiction. And I guess the same logic follows for this thing over here, for this Erlenmeyer flask. If I were to put in some gas particles, let's say over here, they'd have to spread out pretty much evenly. So here you have to consider that collisions in the neck of the flask, right here, would probably be more frequent because there's less space, while collisions down here at the, I guess, bottom of the flask would be less frequent. So here you have more frequent collisions, but it all works out. The reason the collisions are more frequent is because you've got a smaller volume. So if you have more frequent collisions and the particles scatter away from here more often, that's perfect because there is less volume here. So the number of particles occupying a given portion of the volume of this container would still be consistent throughout the whole entire object. Anyway, I hope that made sense. If it didn't make sense, I guess sorry for being a poor explainer. But yeah, the idea is that if you assume that they're not uniformly distributed, then that means they're arranged in such a way that they would have to, at some point, make just the right number of collisions to start, you know, scattering apart. Okay, so there's a weird, challenging conceptual question, which I don't even know if I answered properly, but it's worth thinking about some more, and maybe you can discuss it in the comments. Let's take a look at... Okay, so I do need... Okay, now I know why I labeled this the way I did. Okay, there's something else we have to cover before we can fully answer these. So let me go back to this right here. Oh, actually, before I do that, maybe I should... Okay, let's switch back to the postulates of kinetic molecular theory for a second. And let's use this to justify a bunch of the gas laws that we've seen so far. Specifically, I'm talking about Boyle's law, Charles's law, Gay-Lussac's law, and Avogadro's law. Let's talk about each of those using those 5 assumptions about how gas particles behave. So I think the first one I want to tackle is Charles's law. So Charles's law says that if you increase the temperature, you increase the volume. If you increase the temperature, you increase the volume. So V over T equals something constant. If T goes up, V has to go up in order for the ratio between them to stay the same. Why is it, assuming you're working with a container that has a changeable volume, a variable volume, why is it that increasing the temperature increases the volume? Well, according to, let's see, according to postulate number 5, and I guess I'll put it back on the screen for a second, and maybe you should take a screenshot of this or open this segment of the video in a new tab so that you can have it open in front of you, because I don't want to keep switching to this. But postulate number 5 says the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. When the temperature of the gas goes up, the kinetic energy goes up. What is kinetic energy? It's the energy of motion. So when the kinetic energy goes up with temperature, the speeds of the particles on average will go up as well. So if the particles are moving faster, but their pressure isn't changing, right? Charles's law assumes constant pressure and, of course, a fixed number of particles. If the pressure isn't changing, then that means under postulate number 3, the number of collisions that the particles exert on each other and on the walls is not changing. So if the number and frequency of collisions isn't changing, then the increased speed must be accompanied by an increased wall-to-wall distance in the container. If you don't have that, then if the container doesn't expand, then the increased speed of the particles will lead to more frequent collisions and stronger collisions, which would have resulted in a higher pressure. Okay, so that's an explanation of Charles's law in terms of kinetic molecular theory. What about Boyle's law? What about Boyle's law? So Boyle's law, I'm forgetting how to spell it. Boyle's law says that pressure and volume are inversely proportional. So for example, if I double the pressure, then the volume gets cut in half. Why is that? Why does it make sense that if you decrease the volume of a container, for example, that the pressure would increase, assuming you keep the temperature constant and you keep the number of particles constant? Under postulate number 3 of kinetic molecular theory, we know that pressure is all about collisions. The more collisions that happen between the particles themselves and, of course, with the walls, the greater the pressure is. So if you decrease the volume, then you're shrinking the distance. If you shrink the distance between two walls of a container, and I guess I've got my container right here. So if I were to shrink this distance, if I were to cut this box in half, like so, if I were to cut that box in half and shrink the wall-to-wall distance without changing anything else, I don't change the temperature, so the average kinetic energy and therefore the average speeds of the particles don't change, then if they're still moving at the same speed but they don't have to go as far between one collision and the next collision, they're going to collide more often. More collisions means more pressure, so decreasing volume decreases distance, and under the same kinetic energy, the same speed, you would have more collisions. The reverse is also true. If you expand the volume, then you increase the distance particles have to travel, and if you don't change their temperature, then they have to travel a farther distance at the same speed, so the number of wall-to-wall collisions will decrease, therefore the pressure will decrease. So there's Boyle's law. The Gay-Lussac law, Gay-Lussac's law, which I recently found out is also called Amundsen's law. I have no idea who this guy is, or if it's even a guy. But yeah, pressure and temperature are proportional under constant volume and, of course, constant numbers of particles. So basically, if temperature goes up, pressure goes up. Why? Well, it's all about those collisions. If the temperature goes up, postulate number 5 says that temperature is directly proportional to kinetic energy, or vice versa. And more temperature means more kinetic energy means more speed. More speed without changing the volume means more wall-to-wall collisions. More collisions means more pressure. And of course the reverse is true. If you lower the temperature, particles slow down, collide less frequently, and result in a lower pressure. Pressure is all about how many collisions you have per second and how strong those collisions are. Okay, and then Avogadro's law. Actually, let me think. Would Avogadro's law really be explained by kinetic molecular theory? Well, if you keep the same pressure and temperature, but you increase the numbers of particles, okay, I'll take a stab at it. So Avogadro's law says that the volume is proportional to the number of moles so long as everything else is held constant. So if the pressure and temperature stay the same, so no change in speed because no change in temperature, no change in the number of collisions. If I add more particles and I don't change the volume, then what's going to happen? What would happen if I suddenly injected, for example, twice as many gas particles into this container? Well, there would be more collisions. The only way to prevent that from happening would be to increase the volume so that despite having more particles, there's still enough space between them and between the walls that the frequency of collisions doesn't increase or decrease. So there you go, that's Avogadro's explained in terms of KMT, or kinetic molecular theory. There's one more which doesn't really have a name, but I guess I'll call it the anonymous gas law. I'll call it the anonymous gas law, which we kind of hinted at earlier. Pressure is proportional to the number of moles. So this I kind of already explained while explaining Avogadro's law. If you add more moles but you don't change the volume or temperature of a container, then the pressure would have to increase, because injecting more moles without changing the speed or the distance for the particles traveling would have to result in more collisions. More particles available to make collisions equals more collisions, unless they are either slowed down or have to travel farther. And there you go. There's all the gas laws, all the basic ones, explained in terms of kinetic molecular theory. Now then, what was the other thing I wanted to talk about? So, how temperature affects speed. How temperature affects speed. How temperature affects speed. So I'm going to show you a diagram, a graph, which is called a Boltzmann distribution. And I'm actually going to show you 3 of these, but let me show you this one first. Okay, so that graph you see in front of you is what is often referred to as a Boltzmann distribution. And this graph can be hard for students to read if they don't really spend time thinking about it. It does require some thinking, and back when I was in high school I had to stare at it for a good 20 minutes before I could make heads or tails of what this graph was trying to say. So I'll try my best to explain it, but at the end of the day you will probably still need to spend time thinking about it for yourself and making sense of it. But what you have there is something that's sort of like a bell curve. It's a probability distribution. So on the vertical axis you have the number of molecules that have a given velocity, and on the horizontal axis you have the velocities that those particles can have. So if you take a look at, say, that first dotted line, VP, as it's labeled at the peak right there, that's the most probable velocity. That's not the average velocity, or actually I shouldn't say velocity, but speed. I know they labeled it with velocity, but the physicist inside me wants to call it speed to be on the safe side, because velocity is a vector, and if you don't know your physics, we don't need to get into that. I'm just going to call it speed. But yeah, so VP right there, that's the speed that's most probable for particles. So most particles, the majority of the particles, are going to be at a speed of, it looks like, just under 400. So maybe, I don't know, 380 meters per second, I'd say. I can't really tell by the way that graph is spaced out, but 380 seems like a good estimate. So that's the vast majority of particles. Most particles will be moving at that speed, and then some more particles will be moving, you know, close to that speed. Some will be moving slightly slower, some will be moving slightly faster. And then if you start moving to the right along the curve, you start seeing fewer and fewer particles having higher and higher speeds. And then right towards the end, you have almost no particles at extremely high speeds, like 1200 meters per second or above. So how does this happen? How does this happen? So if you put a bunch of gas particles in a container, the speeds are not distributed evenly. Because if you put a bunch of gas particles in a container, what's going to happen is they're going to have a bunch of collisions. And in every collision, some particles are going to gain speed and some particles are going to lose speed. So it's impossible to keep all the gas particles, you know, even. So the most likely scenarios are some gas particles, the majority of gas particles, are going to hover around some average. So based on the chart that we just saw, it looks like most of the gas particles, I'd say over 80% of them, fall between 200 to, it looks like 800 meters per second. So 200 to 800 meters per second seems to be where the majority of gas particles in that chart were. But you do have the extremely unlucky particles. Let me pull the chart up again. You do have a few extremely unlucky particles that happen to collide with other particles in such a way that they always or mostly end up losing energy. They end up losing speed and giving it to other particles. On the other hand, if you look at the right-hand side of the chart, you see a small minority of really, really lucky particles that have a lot of speed. They usually or always gain speed from every collision that they have. So when those faster particles collide with slower particles, eventually you can't have too many of them, because what's going to happen is once you get a few particles that are moving at really high speeds, I guess I should probably try to illustrate this. I'll do it on another sheet. So let's say, for example, let me just do something really simple. Let's say I've got 10 particles. Let's say I've got 10 different particles, and I probably should have planned this out better. Let's say I've got 10 different particles, and here's the different speeds that they have. So I guess over here I'm just going to number the particles, so this isn't really even an axis. So here's particle 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, 1, 5, 10. So let's say you have a bunch of different particles, and let's say here you have a bunch of different possible velocities. I'll just keep the numbers small and simple. So 1, 2, 3, 4, 5. Okay. Let's say you have that one unlucky particle that only has a speed of 1. And then you have a couple particles at a speed of 2. So let's say particle number 2 and particle number 3 have a speed of 2. And then let's say you've got particle number 4 has a speed of 3. And so does particle number 5. And so does particle number 6. And then particle number 7 has a speed of let's say 4. And then particle number 8 also has a speed of 4. Same thing for particle number 9. And let's say particle number 10 is the only one left that manages to reach a speed of 5. Now, if particle 10 is going to collide with any of the other particles, it's always going to be colliding with a particle that has less energy. So, it is much more likely that when particle number 10 collides with any of these other 10 particles, or any of these other 9 particles, I should say, it's much more likely that particle number 10 is going to lose energy. If you have energy, usually the most likely thing to happen is you're going to lose it at the next opportunity. If you want to gain energy, number 10 is better off finding a particle that's moving at faster than 5 meters per second. Let's say this is speed in meters per second. And of course, since it can't find any, it's not going to keep its crown for much longer. So in all likelihood, particle number 10 is probably going to collide with, say, I don't know, one of these particles over here, for example. So let's say it collided with particle number 6. Particle number 6 would probably gain some speed. Maybe it would bump up all the way to 5, or maybe it would, just be bumped up to a 4. And then that would bring 10 down to a 4 as well. But now that you have a lot more 4s, one of these, let's see, you've got 1, 2, 3, 4, 5 particles that are moving at 4 meters per second. So there's now a greater likelihood that 2 of these are going to bump into each other, and no matter what, one of them is going to lose energy and the other is going to gain. Well, on rare occasions, maybe they bump into each other and their energies stay the same and their speeds don't change. But in all likelihood, if any 2 of these bump into each other, then one of them is going to give some of its momentum and some of its speed to the other. So one is going to gain and one is going to lose, and congratulations, you've created a new particle that has a speed of 5. So let's say, for example, particle number 7 collides with particle number 8 next. And let's say 7 ends up drawing the losing stick and loses 1 unit of speed, while particle number 8 ends up gaining it. Well, now particle number 8 is the new king of the hill, so to speak, until, of course, it collides with any of these other 9 particles that have less energy. A similar story can be said of particle number 1 here, which has the lowest energy. There are very few particles at the bottom of the hill, for the same reason there are very few particles at the top of the hill. Because if you're at the bottom, then the most likely thing that's going to happen, in fact, the only thing that can happen, is colliding with another particle that has more energy than you do. So when particle number 1 collides with any one of these other particles, it doesn't have any more energy to lose. It's practically lost everything it has. So what's most likely to happen is it's going to gain energy and siphon it off of one of these other particles. So that's why the extremes, the lowest speeds and the highest speeds, are the rarest, because if you're at a really low speed, you're most likely to collide with particles at a higher speed than you, which means you'll gain energy from them. And if you're at the highest of speeds, then you're more likely to collide with particles at lower speeds and give energy to them. So the most common speeds are the ones that are somewhere in the middle rather than at the extremes. This will require a little bit more thinking to really wrap your head around, but I hope that this kind of helps illustrate what's going on with the Boltzmann distribution. Okay, speaking of the Boltzmann distribution, so there's another dotted line over there which is labeled U sub RMS. This isn't really something that most students need to know. If you're in high school, you definitely don't need to know about the RMS speed of gas particles. If you're in college, you might need to know about it. But it's kind of like the average, but not quite. It's kind of an average speed, but not quite. So here's how RMS speeds are calculated. The formula requires some substantial physics knowledge to derive, so I won't show you the derivation, but I will give you the formula. So the formula for the RMS speed is square root of 3 times RT over the molar mass, and this molar mass has to be in kilograms per mole. Has to be in kilograms per mole, because really this is from physics, and in physics the standard unit for mass is kilograms and not grams. But yeah, without a background in physics, I can't really explain this properly to you, why it makes sense or where it comes from, but that's just what it is. I can show you a rough calculation. Let's say I have 3 gas particles, or 4. Let's do 4 gas particles. So one of them has a speed of 200 meters per second. The other one has 300 meters per second. Another one moves at 250 meters per second. And a fourth one moves at 350 meters per second. Let's say I've got 4 gas particles like that. Okay, let's say I want to calculate their average speed. We know how to do that. You add up all the numbers and you divide by the number of numbers. So I do 200 plus 300 plus 250 plus 350 divided by 4, and that should give me, let's see, 200 plus 300 plus 250 plus 350, divide that by 4, and I'm getting 275. So the average is 275 meters per second. That's the average speed. Okay, what is the RMS speed then? How do I calculate that? Well, if you know the exact number of particles and their exact velocities, which is very unlikely when you're dealing with millions and billions of particles, then what you can do is you can take the root mean square. That's what RMS stands for. You square the velocities, so I would do the root mean square speed. Did I say velocity earlier? Speed. Root mean square. The root of the average or mean of the squares. So root of the average of the squares, so 200 squared plus 300 squared plus 250 squared plus 350 squared. So that's the sum of the squares, and then if I take the average of the squares, I'm just dividing that total by the number of particles, which is 4, and then the root of that is your root mean square value. So this is kind of an average. I mean, you're squaring things, yes, and then you're taking an average, and then you're unsquaring by taking the square root, but the square root doesn't distribute over addition, so this won't be exactly the same as the average. if I plug this into my calculator, then I've got 200 squared plus 300 squared plus 250 squared plus 350 squared divided by 4, and then take the square root, and I get 280.62. I get 280.62. And of course I'm not being careful with my sig fig rules here, but I'm kind of just using this as an example to illustrate a point. So the RMS speed is usually going to be a little above the actual average speed. And the reason that it's used is because calculating average velocity doesn't really work. RMS values are used in cases where the average would inevitably be 0. So with gas particles, if you wanted to calculate the average velocity rather than the average speed, you'd have to take the direction into account. But if the particles distribute their velocities nearly evenly, then you're going to have just as many particles moving left as you have moving right. You're going to have just as many particles moving up as down. You're going to have just as many particles moving forward as you do back. And all of those velocities, if you add them up, taking into account their directions, then the total velocity is 0. If you add all the positive velocities to all of the negative velocities, which you know exist in equal amounts and exist in equal likelihood, then you can't really get an average. So that's typically where RMS values are used, in cases where taking the average would give you a 0, squaring and then taking the average would eliminate the negatives, but it would also not give you, you know, your proper average. So that's why we use it. But I don't think you're going to need to worry too much about this, even if you are in college, unless you have a professor who also happens to be your physics professor. They probably won't care too much about this, but what do I know? Look in your syllabus or ask your professor how much they care about this. Anyway, that's RMS speed. Let's take a look at another Boltzmann distribution. Kind of a weird segue, but let's take a look at how temperature affects the Boltzmann distribution. So here you've got a bunch of different Boltzmann curves, and each one is a curve at a different temperature. So you'll notice the narrowest, tallest one of these curves is at the lowest temperature. And you notice as you increase the temperature, the curve gets flatter and smoother and wider. So why does this happen? Well, when you increase the temperature, more kinetic energy is available. When more kinetic energy is available, then some of those unlucky particles from before that had extremely low velocities, well, now they get to join the high velocity club, or high speed club, I should say. I keep on saying velocity when I should say speed to be on the safe side. So more of those low-end particles can start moving up, migrating up into the high-speed categories. Meanwhile, the fastest particles, the ones that were already getting high speeds, they'll get a boost too. They'll have an opportunity to reach even higher heights, but they're not going to get as much of the benefit because, well, the benefit of the increased temperature and the increased available energy has to distribute over all the particles, and if you're in the minority of the particles, you're not going to gain as much of the benefit. Most of the benefit is going to go to the majority of the particles, which are closer to the middle. So that's why this curve tends to smooth out as more energy becomes available. Of course, you will still have particles that are really, really close to having no speed at all. That can always happen if the right sequence of collisions takes place. It's rare, but possible. especially when we're talking about billions of particles. But yeah, just remember that part. Whenever the temperature increases, the curve kind of smooths out and flattens out and gets wider, and of course the top speed does get higher. You notice the first curve, the 100 Kelvin curve, seems to stop a little past 500 for the maximum speed, and then the 200 Kelvin curve has a maximum speed that's just under 1,000. Then the 500 Kelvin curve has a maximum speed that is nearly 1,500. And then the 1,000 Kelvin curve, they couldn't even draw the rest of the graph. It probably reaches near the 2,000 meter per second speeds, maybe even higher. But there's the effect of temperature on the Boltzmann distribution and on the speeds of particles. So when the temperature does go up, the average speed does go up because all of the speeds go up a little bit. The curve smooths out more. Let's take a look at one more of these. One more group of Boltzmann distributions. Okay, so here we don't have different temperatures, but instead what we're doing is we're changing the actual gas that we're using. And what that should mean to you is that we're changing the mass of the gas. So when we compare heavier gases and lighter gases, we see that the lighter gases seem to behave like the high temperature curves from the previous shot that we looked at, from the previous set of curves. So helium seems to be the lightest of all the gases that we've got. They're all noble gases in this picture. Helium, neon, argon, krypton, and xenon being the heaviest. So if the particles are lighter, then the speed distribution is flatter, and more importantly, the maximum speed is higher. The average speed and the maximum speed are higher when the gas has a lower molar mass. The lighter the gas is, the faster it moves, and that's a pretty intuitive idea. So that part I definitely want you to remember. The lighter the gas, the quicker it can move. Not too hard to imagine why something heavier would have trouble moving fast. Okay, and I think that's everything for Boltzmann distributions. Let's go back to these kinetic molecular theory questions. Hold on, I feel like I'm forgetting one more thing. Okay, there is one more thing I'm forgetting, but I think it can wait. So, number 91. Can the speed of a given molecule in a gas double at constant temperature? Explain your answer. So, this can be a bit of a trick question sometimes, but it really depends on how it's worded. So in this case, if the temperature is held constant, if the temperature is held constant, the average kinetic energy is constant, and if the average kinetic energy is constant, then the average speed is also constant. But that's not what they're asking about. They're asking about the speed of a given molecule, just one specific molecule out of millions of billions. Can its speed double at a constant temperature? And the answer is yes. Yes, it can. Because, for example, I could have, going back to this over here, I could have my unlucky particle number 1 collide with, say, particle number 2 without the temperature changing, and it could pick up enough energy to double its speed It could pick up enough energy to double its speed without the temperature really needing to change. The total amount of energy, the total momentum that's possible for the whole box of particles isn't changed, it's just changed for an individual particle. So yes, you can have an individual molecule double its speed, unless it happens to be at one of those extremely high speeds where it doesn't have much chance of doubling its speed. Okay, 92. Describe what happens to the average kinetic energy of ideal gas molecules when the conditions are changed as follows. Part A, the pressure of the gas is increased by reducing the volume at constant temperature. Okay, we already talked about this when I was explaining all of the smaller gas laws in terms of KMT. Right? If the volume is reduced at constant temperature, then the reason the pressure increases is because you've got shorter wall-to-wall distances with no change in particle speeds, or average particle speeds, I should say, which means that you would have an increase in collisions, which leads to an increase in pressure. B, we've got the pressure of a gas is increased by increasing the temperature at constant volume. So that was what I said for Gay-Lussac's law, if I'm not mistaken. Yeah, if you keep the volume constant, increase the temperature, faster moving particles will collide more frequently, resulting in a higher pressure reading. And then C, the average velocity of the molecules is increased by a factor of 2. Okay, this we need to be careful about. So unless you know your physics, you wouldn't really know how to do this one. But in physics, the formula for kinetic energy is 1/2 the mass times the speed squared. So if I double the speed, then the kinetic energy is not doubled, it's quadrupled. If I should say average, if I double the average speed, then I quadruple the kinetic energy, because if I replace V average with 2 times V average, then the new kinetic energy, I'll call it KE star, would be equal to 1/2 mass would stay the same for an individual particle, and I would replace V average with 2 V average and square that, and if I square it, 2V average times 2V average is 4V average squared. So it would be 1/2 mV average squared all times 4. So the new kinetic energy would equal 4 times the original kinetic energy if I double the average speed. Now, the average kinetic energy is directly proportional to the temperature. So average kinetic energy is directly proportional to the temperature. If I'm not mistaken, it's equal to 3/2 R times T. Again, this is another one of those equations where you're going to need a background in physics in order to be able to prove it, but the point is average kinetic energy equals a bunch of constants times temperature. So kinetic energy varies, or average kinetic energy varies linearly with the absolute temperature, but the speed, the square of the speed, is what varies directly with the kinetic energy. So I guess you could say that every time you quadruple the temperature, the average speed is doubled. So yeah, very important to remember that doubling the absolute temperature doubles the average kinetic energy, but does not double the average velocity. Instead, it would increase the average velocity by a factor of square root 2, so less than double. Okay. So, part C, it was asking the average velocity of the molecules is increased by a factor of 2. That means that the kinetic energy is increased by a factor of 4, which would mean that the temperature would have increased by a factor of 4. 93. The distribution of molecular velocities in a sample of helium is shown in the figure. Was that the one that... Let me see, was that the same one that we had over here? Okay, yeah, it was. They're referring to this. Okay, so it says, if the sample is cooled, will the distribution of velocities look more like that of hydrogen or of water? Will it look more like hydrogen or water if the sample is cooled? Okay, so we need to take into account what we saw with the different Boltzmann distributions that we looked at earlier. So if the temperature is decreased, what does that do? It makes the curve narrower and taller. So let me go ahead and pull that up so we can look at it again. So if it's cooled, then it gets narrower and taller. Lower temperatures, you get taller spikes and narrower a narrower range of possible speeds. On the other hand, if we consider the different masses, so if we consider water versus hydrogen gas. Hydrogen gas is lower in molar mass than helium. So following the pattern seen in this graph, H2 would be further to the right and wider. Meanwhile, water is much heavier than helium. The molar mass of water is approximately 18 grams per mole, while helium is just about 4. So water would be probably somewhere between neon and argon. Well, neon and argon, compared to helium, are sharper, narrower peaks. And we already know if you cool helium, we know from the temperature curves we saw just a minute ago, that lower temperatures means narrower, sharper peaks. So it looks like cooling helium would make it look like would make it look more like water than hydrogen gas. So going back to the problem, comparing it to hydrogen gas versus water, we know that the curve would be skewed to the left and get sharper and taller because of cooling. So helium would start looking more like a heavier gas rather than a lighter one. So it would look more like H2O, not H2, and that takes care of that one. Let me see. So next up, I've got this set of problems. Let's take a look at them real quick. What is the ratio of the average kinetic energy of a sulfur dioxide molecule to that of an oxygen molecule in a mixture of two gases? What is the ratio of the root mean square speeds of the two gases? Okay, so for this we need to talk about Graham's law of diffusion. So for this we need to talk about Graham's law of... Actually, no, we don't. We can talk about Graham's law of diffusion later. We can do this just using the equations that I've given before. So, yeah, let's go ahead and do that. First question is, what's the ratio of the average kinetic energy of a sulfur dioxide molecule to an oxygen molecule in a mixture of two gases? Well, if they're in the same mixture, then they ought to be at the same temperature, which means they ought to have the same average kinetic energy. Oh, trick question. The ratio is 1 to 1. If they're at the same temperature, they have the same average kinetic energy. What about their average speeds, or in this case, their root mean square speeds? How do those compare? So having the same average kinetic energy does not mean having the same average speed, because of mass, right? Kinetic energy, or average kinetic energy, is 1/2 the mass times the average speed squared. So the heavier the particle, if you've got the same kinetic energies for both, but one has more mass, then it has to have lower average speed in order for the product to be the same for both gases. So for the qualitative answer, the sulfur dioxide would be slower because it has more mass. Even if they have the same kinetic energy, the sulfur dioxide would be slower than the oxygen because it's heavier. That being said, we want to get the ratios of their speeds, and I guess we could do that just using this, or we could use this equation. So either option should be fine. Maybe I'll do it both ways just to illustrate the point. Let's see, so we've got, actually, yeah, I'm just going to directly compare the RMS values for sulfur dioxide over oxygen gas. And I'm going to skip over the kinetic energy based calculation. If you really want to do it, then feel free to do so, but I don't want to spend too much time on the most unnecessary stuff. So we've got square root of 3 RT over M, and this is going to be for SO2 specifically, while this over here is the square root of 3 RT over the molar mass of oxygen. Remember, in this equation, molar mass needs to be in kilograms per mole, though since I'm calculating a ratio, it won't really matter because the units are going to cancel out anyway. So I guess for this, we'll stick with grams per mole. But yeah, let's see. So, of course, the ratio of two square roots is the square root of the ratio. So this is equal to square root of 3 RT over molar mass sulfur dioxide over 3 RT over molar mass oxygen. The 3 RT cancels out, and what I'm going to be left with is the square root of 1 over the molar mass of SO2 divided by 1 over the molar mass of O2. If I divide by 1 over the molar mass of O2, that's the same as multiplying by the molar mass of O2. And there we go. Let's compare. So we've got molar mass of oxygen gas is 31.998. Molar mass of sulfur dioxide, so it's got O2 in it, so that saves us some time. And then sulfur is 32.066. So 32.066 plus 31.998 is 64.064. And that's going to equal, let's see, square root of 31.998 over 64.064 is 0.7067. Let's just take 4 sig figs here. I guess we should be keeping 5. Okay, 0.70673. Alright, so basically what this means is that the speed of the sulfur dioxide particles, the average speed, or, well, yeah, the ratio of the root mean square speeds is also going to be the ratio of the average speeds. I'm pretty sure that would be the case. But you can confirm using the kinetic energy method instead, and I would expect you get the same result, but if you get a different result, leave a comment and discuss it. But yeah, it looks like on average, sulfur dioxide molecules travel at about 70% of the speed of oxygen molecules in the same mixture under the same temperature. Alright, let's take a look at the other problem. What does it say? A 1 liter sample of carbon monoxide initially at STP is heated to 546 kelvins and its volume is increased to 2 liters. Okay, what effect do these changes have on the number of collisions of the molecules of the gas per unit area of the container wall? So temperature was increased. That increases kinetic energy, which increases speed, which increases the number of collisions. The volume was also increased. That increases the distance that particles have to travel between walls before 2 consecutive collisions, and therefore reduces the total number of collisions and would lower the pressure. So that's part A. Part B, what is the effect on the average kinetic energy of the molecules? Let's see, I guess it's doubled. At STP, the temperature is 273 kelvins, and 546 kelvins happens to be exactly 2 times that. So the average kinetic energy is doubled. What is the effect on the root mean square speed of the molecules? So, again, correct me if I'm wrong, but the effect on the root mean square speed is proportional to the effect on the average speed. And if the average kinetic energy is doubled, the average speed would increase by a factor of 2, and if the average speed increases by a not a factor of 2, a factor of square root 2, I should say. And if the average speed increases by a factor of root 2, then I would imagine that the RMS speed also increases by a factor of root 2. Let me think. If I actually go back to my RMS sample calculation, what if I did if I increased this by a factor of root 2, then that would be the same as multiplying each of these by root 2 and then adding them and dividing them by 4. Okay. And then if I multiplied each of these by root 2 and then squared them and then divided them by 4 and then took the square root, then that would be a common factor of root 2. Yeah, okay. Yeah, I'm now 100% sure. Whatever factor increase or decrease happens to the average velocity. Oh, you didn't see my reasoning, did you? Oh well. What I did, I'll just show you real quick. I just went back to this calculation here and kind of mentally went through what would happen if I wanted to increase U average by root 2. That would mean multiplying each of these by root 2. And then if I did the same thing here, multiplied each of these by root 2 before squaring them, then ultimately I'd have the same result times square root 2. So yes, whatever factor of increase or decrease you have on your average speed, that same factor increase or decrease will apply to your RMS speed. Okay, but going back to the problem, so effect on average kinetic energy, we already said. What's the effect on the root mean square speed? It would increase by a factor of root 2. And that's it. That takes care of that one. Let me see, where do I want to go from here? So I did mention Graham's law of effusion. Let's go ahead and talk about that. Actually, let's talk about effusion and diffusion. You finally get to figure out why I had a beaker on my table earlier. So, do I have any visuals for this one? No, I do not. Interesting. Okay, well, let's talk about effusion and diffusion. So, diffusion, if you're taking biology, you might already know what it is, but I'm just going to show you what it is right here. Beaker full of water. I know, everybody's favorite experiment. So exciting, it's water. So, beaker full of water. I'm going to put 1 drop of red food coloring in here. And what you're seeing right now, the way that the red food coloring is kind of just spreading outward, that's called diffusion. If I were to leave it here, then eventually, without me stirring this thing or disturbing it in any way, the red dye molecules would eventually distribute themselves evenly throughout this water. Why does that happen? Well, because the molecules of the red dye are going to move around in the water. At first they move around slowly, as you can tell. This isn't happening really quickly, but they move around, and eventually they, just like the gas particles, they will have a bunch of different collisions, and eventually, if they're too crowded in one place, they're going to collide with each other so much that they'll, you know, start repelling each other outwards in every which direction. And before you know it, after enough time has passed, you do end up with a situation where they're pretty much evenly distributed. Ooh, there's still a clear spot in there. Are we going to wait to see how long this is going to take to fully diffuse? Or should we just move on to diffusion and effusion? I think I'm just going to go ahead and... there. End your suffering. Oh, actually, still looks like it's unevenly distributed. I don't know if you can see that on the camera, but there are still parts that look denser and darker than other parts. Anyway, that's diffusion, and that's pretty much all you need to know about it. So there's diffusion. You just need to know it as a concept. Diffusion is when a gas, or in my example, a liquid, just kind of disperses itself within the available space. So diffusion is when something, when a fluid disperses within the available space. Diffusion is how smells spread from the kitchen to every other room in the house, and how you know that dinner is almost ready. Diffusion is also how air refresheners work, and how... what else can I think of? What are those things called? Those... I think they would still be called air refresheners, right? You plug them into the wall in a room, and they just kind of squirt some air outward. So diffusion is when fluid particles, fluids could be gases or liquids. I know we usually use the term fluid in common English to mean liquid, but fluid is a word for anything that flows, and so it includes both liquids and gases. Remember that, especially if you're taking AP Physics 2. you will be spending a lot of time studying fluid mechanics. But yeah, that's diffusion. So diffusion is when the fluid just kind of spreads. Effusion, on the other hand, is similar but not quite the same. Effusion is when a gas, I don't know if it also applies to liquids, I imagine it would, but to be on the safe side I'm going to say gas instead of fluid. When a gas escapes a container through a small opening. Escapes a container through a small opening. So effusion is what happens when, say, you spray perfume. When you use one of those perfume spray bottles, you know, the ones that you have to like squeeze the bulb to get the perfume out. That would be an example of effusion, because you've got, well, actually, maybe a spray bottle wouldn't be the best example, because technically we're working with a liquid there. But I guess it's still the same concept. Okay, let's do this one. Let's do this as an example. Let's say you are let's say you've got, say, a tire and a hole gets poked in it. Or, well, let's say a balloon that's not so inflated that it would just outright pop. Let's say you've got a balloon and you poke a hole in it such that it doesn't instantly pop. So you poke a hole in a balloon. It doesn't instantly pop. Instead, it just kind of, you know, you can sometimes hear that sort of fizzing sound of the air just gradually, you know, flooding out. That would be an example of effusion. Or, when you pop something like a beach ball, say. I think that's much more common. If you poke a hole in something like a beach ball, or just try to deflate a beach ball, though I guess in that case you're not really poking a hole in it, you're just kind of forcing the air out. But anyway, you get the idea. Effusion is the escape of a gas through a small opening in its original container. So there is an equation called Graham's law of effusion, which is kind of similar to what we did here, actually, where you can compare the rates of effusion, how quickly a gas is escaping from a container, on the basis of their molar masses. So Graham's law of effusion, and I see I'm going to have to start restocking my paper pretty soon. Oh, the number of trees that have to die for my satisfaction. Let's use this one instead. So Graham's law of effusion. Graham's law of effusion says that the escape rate, the effusion rate of gas 1 over the effusion rate of gas number 2, so the ratio between the gases, is inversely proportional to the square root of their molar masses. So rate 1 over rate 2 is equal to the square root of molar mass 2 over molar mass 1. A lot of equations we've been seeing in this part have been, you know, 1, 2, 1, 2. Not this time. This time it's 1, 2, and then 2, 1. It's very easy to get tripped up, especially when you think of the pattern that was established by most of the other equations we covered today. Definitely hard to remember this, so, you know, take a mental note and remember that In Graham's law of diffusion, it's kind of the reverse of your intuition. Now, a lot of students get tripped up when using Graham's law of diffusion because they often feel like they have to calculate R1 or R2. But usually, Graham's law problems don't want you to calculate either of these. They just want you to calculate the ratio between them. And then you can stop at that. You don't have to identify R1 or R2 specifically. So let's take a look at a couple of problems here based on Graham's law of diffusion, and then we'll talk about real gases for a bit, and then we'll wrap things up. Okay, so which of these problems do I want to cover? 81 says a balloon filled with helium gas takes 6 hours to deflate to 50% of its original volume. How long will it take for an identical balloon filled with the same volume of hydrogen gas instead of helium to decrease its volume by 50%? Okay, so the 50% part isn't really the most relevant part. It's the amount of deflation. So the amount of deflation depends on the rate of deflation. It depends on the effusion rate. And the effusion rate is not constant. It's going to change over time because you've experienced it yourself. If you've ever, emptied out the air from a balloon or a beach ball or something like that, you notice at first, you can even hear it. You can hear the air is escaping really fast at first, but as the container, as the beach ball or balloon gets emptier and emptier, the sound of the gas gets quieter, and you can feel the gas is just coming out slower and slower and slower until eventually it's coming out at a trickle, and then finally it's completely deflated. In fact, what you probably do in response to this is you apply more pressure to squeeze the gas out faster because of how quickly it starts to slow down. So we're going to ignore all of that and not worry about it. We're going to say that for both of these cases, whether it's with helium or with hydrogen, that the ratio of the effusion rates stays the same, and that they both, drop off in their effusion rate by an equal factor at equal times. Maybe I'm making this sound more complicated than it needs to be, but for the people who care about the particulars, I think you got the message. For the people who don't care, you can retroactively tune out what I just said. All that we need to focus on for problem 81 is figuring out the ratio of the effusion rates between helium and hydrogen. So let's go ahead and do that. All you have to do is use Graham's law of diffusion. So helium is heavier, so I'm going to make helium go on the top. It just makes more sense to me to put the... Actually, wait. No. I'll put the lighter one on the top because it'll be faster. So hydrogen is lighter. So I'm going to do hydrogen over helium. That way I get, numbers greater than 1. It's just easier for me mentally to process that. So I'm going to put the faster one over the slower one. Whenever you have the choice, that's what I would recommend, so that your ratio of rates is always 1 point something or larger. Okay, and that would be molar mass of helium over molar mass of hydrogen. Should this be in grams per mole or kilograms per mole? In this case, it doesn't matter because the units are going to cancel out. As long as you use the same units for both, you'll be fine. So helium is roughly 4. In fact, if I look it up, I'm getting 4.003 grams per mole. Over hydrogen would be 2.016 if you count both hydrogens. That's roughly going to be square root of 2, which reduces to, let's see, square root of 4.003 over 2.016 is about 1.409. 1.409. Okay, so that's the rate of hydrogen escape over the rate of helium escape. So the hydrogen escapes 1.409 times as fast as the helium does, which means it should take less time to deflate the balloon by 50% if the balloon was filled with hydrogen rather than helium. So helium took 6 hours, and helium is 1.409 times slower. So if it took 6 hours for helium, then just using the logic of proportions here, with hydrogen, let's see, well, I guess you could say rate times time. So if you take escape rate times time, then escape rate of helium times the time for helium equals the total amount of particles that have escaped, which would be 50% deflation. To get 50% deflation with hydrogen gas, you'd have to have the rate of hydrogen times the amount of time for hydrogen would have to be equal. So the amount deflated should be equal for both of them. So then we can say, if I divide both sides by the rate of helium, actually no. Do I? Yeah, let's do that. Divide both sides by the rate of helium. The time for helium equals rate of hydrogen over rate of helium times the time for hydrogen. That H was a little too big to be a subscript. I'll just make the T bigger to compensate. We already know what this is. This is 1.409. So time for helium was 6 hours equals 1.409 times the time for hydrogen. I'm sure some of you already knew what to do here, and we're already dividing 6 by 1.409, but I wanted to write this just in case for the students that didn't quite get the logic here. 6 over 1.409 gives me about 4.258. Let's say that the 6 hours was exact, so the hydrogen-filled balloon would take 4.258 hours to complete, or to 50% empty out. And of course, a bonus question that I'll ask is, will it take 6 hours for the helium-filled balloon to completely empty out after reaching the halfway point? I already kind of answered it before. It takes 6 hours for the helium balloon to be half deflated. It will not take another 6 hours to deflate the other half. It'll take more than 6 hours, right? Going back to what I said about how the effusion rate will gradually start going down as less gas particles are left inside the balloon or whatever container you may have. You know that from common sense and personal experience, I'm sure, if you've ever deflated any inflatable object. But yeah, let's take a look at some more here. 82 says, explain why the numbers of molecules are not identical in the left and right hand bulbs. Okay, that pertains to a figure that I do not have, so we'll skip on that. 83, starting with the definition of rate of effusion and grams, finding relating rate and molar mass, show how to derive the Graham's law equation relating the relative rates of effusion for two gases to their molecular masses. So you can look that up in your book. I'm pretty sure it's very similar, if not identical, to what we did right here. So I'm pretty sure it's similar to, if not exactly the same as what we did here. I'm just not remembering right now exactly what the equation for rate of effusion is for a single gas, but that just goes to show you how I guess insignificant Graham's law is in most chemistry courses. It's not talked about enough that I would need to know everything about it to teach my students, because, well, they don't ask about it often enough. Usually it's just a classic problem like the one we just did with the 6-hour deflating balloon. But, you know, for the people who care, you can definitely look up the original equation for the rate of effusion of a single gas and do the math and figure it out for yourself. Number 84, heavy water, D2O. So the D, you might notice on the periodic table, there is no element D. So the D stands for deuterium, which is another name for the second isotope of hydrogen. The most common form of hydrogen is hydrogen 1, but there's also hydrogen 2 called deuterium, which is sometimes given the element symbol D. So that's what the D is for. It's a hydrogen atom with one neutron in addition to the proton that every hydrogen has. The other isotope of hydrogen is tritium. I think I mentioned it before in another video. It was one of the focal points of one of the Spider-Man movies. But anyway, heavy water, which is just two hydrogens replaced with deuterium specifically, that specific version of hydrogen, has a molar mass of 20.03 grams per mole. It can be separated from ordinary water as a result of the difference in the relative rates of diffusion of the molecules in the gas phase. Calculate the relative rates of diffusion of H2O and D2O. Okay, so that one should be really quick and simple. I'll just set it up and stop there. I think I can fit all that right in here. Okay, so let's say rate of water, ordinary water, over rate of heavy water. That's going to be equal to the square root of the molar mass of deuterium, or not deuterium, heavy water, I should say, 20.03, whoops, 20.03 over the molar mass of regular water, which is approximately 18.02. I know I'm rounding a bit there, but there you go. There's the setup. You can plug that into your calculator and get the answer, and you're done. Okay, what's next? 85. Which of the following gases diffuse more slowly than oxygen? Okay, so this one you should be able to do without a calculator. You should be able to look at the periodic table and make a little bit of an estimation for some of these molar masses, but basically, the higher the molar mass, the slower it is. The lower the molar mass, the faster it is. Should be really, really simple if you just line them up and arrange them in order of decreasing or increasing molar mass, whatever floats your boat. And yeah, figure out where they're placed compared to oxygen. All the ones with more molar mass than oxygen are faster, are slower. All the ones with less molar mass than oxygen are faster. End of story. I don't think you need me to go through that one. 86 looks kind of messy. 87 says calculate the relative rate of diffusion. I mean, diffusion is kind of similar to effusion, so I wouldn't be surprised if the relative rates of diffusion obeyed Graham's law, but we'll skip that one. Do I need to know any of these? Or do I need to cover any of these? I feel like they're unnecessary. 88 looks interesting. What about 89? Ooh, 89 looks interesting, but maybe in the interest of time we should skip over it. Okay, let's do number 88, and then we'll talk real quickly about real gases, and then we'll end the video. So 88 says, a gas of unknown identity diffuses at a rate of 83.3 milliliters per second in a diffusion apparatus in which carbon dioxide diffuses at the rate of 102 milliliters per second. Calculate the molecular mass of the unknown gas. So you can still use the ratio of the square roots of the molar masses here. I hope. If I look it up later and it turns out that what I'm doing here is wrong, then I'll point it out. But I'm pretty sure that we can still use Graham's law of diffusion for diffusion problems as well. Let's see, so the unknown is 83.3, the carbon dioxide is 102, so I'm going to put 102 on top over 83.3. So carbon dioxide unknown, which means carbon dioxide should go here, and the unknown, I'll just call it X, goes there. Okay, if I square both, well, first divide 102 by 83.3, and there's 1.22. 1.22 equals the square root of molar mass X over molar mass of carbon dioxide is, let's see, 12.011 plus 31.998 is 44.009. Okay, square both sides, so 1.22 squared is 1.49 approximately, equals, if I square the other side, that just gets rid of the square root, so molar mass of X over 44.009, multiply that in, 44.009 times 1.49, whoops, what did I do? Forgot to hit the multiplication button. And that's 65.6. So molar mass of the unknown gas is about 65.6 grams per mole. Now, if they told you that this gas was monatomic, then you could probably look in the periodic table and find something with a molar mass close to this, and that would be your gas. But for all I know, this could, well, it's most likely a polyatomic gas, and it'll be kind of hard to figure out which gas it would be if it really is polyatomic. But if it's monatomic, just looking around here real quick, I don't see anything that stands out. So yeah, it's probably a gas that's made of multiple elements. But there are problems where they might ask you to go a step further and guess what the gas is, if, you know, it's fair enough of them to ask you, if there's enough information available that you could guess it without, you know, wasting too much time on a wild goose chase. Okay, I think that is it for Graham's law of effusion. Now let's go ahead and talk about the behavior of real gases. So, of course, all this time we've been working under the assumption that our gases behave ideally. That's not really true. Gases don't really behave ideally, and the reasons are actually pretty simple. We'll get to know the reasons more and more as we learn about Lewis structures and the shapes of molecules, and the polarities of molecules and all that stuff. But for the time being, what you need to know is that under the assumptions of kinetic molecular theory, one of the assumptions we made is that the collisions are completely elastic. They conserve energy. There's no attractive or repulsive interactions between the gas particles when they collide with each other or when they just go near each other in general. And that assumption is not correct. Another bad assumption we make is we assume that the volume of the gas particles is negligible in comparison to the container. And so we end up assuming that the volume available for the gas particles to move in is equal to the whole volume of the container, when really it should be the volume of the container minus, the size of the gas particles. Even if they're small, they do subtract from the total available space for the particles to move around in, just by virtue of their own size. So here's a graph that measures something that chemists care about called compressibility. You don't really need to know about it. There is an equation up there at the top that shows you how they calculate it, 2 different ways of calculating it. And basically, it's the actual volume of a gas under a certain temperature and pressure divided by the predicted volume of that gas according to the ideal gas equation. And what you see on that graph is as the pressure goes up, it seems like the compressibility also tends to go up. It goes down a little bit at the beginning, and then it starts to just go up, and it deviates from ideal behavior. Ideally, the compressibility should be 1. The actual volume should be equal to the volume predicted by the ideal gas equation, which is that light blue line in the middle of the graph. No gas actually behaves like that. So you might wonder, why is it that we use the ideal gas equation at all, and how do we correct for this mistake? So there are a couple of things you could do that can make a gas behave more ideally. It turns out that real gases behave closest to ideal under really, really high temperatures and really low pressures. But before we explain why that works, maybe we should review the assumptions of kinetic molecular theory and talk about what is screwing with this graph right here. So let me go back to the assumptions of KMT. So assumption number 1, one of the problems with it is the part where it says changing direction only when they collide with other molecules or with the walls of a container. That's not entirely true. For some gases, the gas particles are going to have some polarity to them, which basically means they kind of behave like magnets, except it's electricity rather than magnetism. So they can push or pull each other just through these attractive and repulsive effects, similar to how magnets behave. Without them having to touch each other, they can affect each other. So that messes with the motion of particles a little bit. Assumption number 2, the molecules are negligibly small. We already talked about this. We can't actually get away with neglecting the sizes of the gas particles themselves. That has to be subtracted out of the total volume of the container, unless the container is really, 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 really big and you only have a few gas particles. And of course, the word "a few" should be taken as a relative concept. A couple million particles could still be considered a few. Assumption number 3, pressure as a result of collisions. Yeah, that one's fine. Assumption 4, gas molecules exert no attractive or repulsive forces on each other. This is wrong, because a lot of gas molecules might have some polarity to them which could interfere with the collisions. The collisions may not be perfectly elastic. There could be loss or gain of energy in these collisions that you wouldn't expect if you just treated them like, say, normal collisions between billiard balls. And then assumption number 5, that's fine, that's just defining temperature. So yeah, there's the different flaws. So basically, the volume thing, that's easy to account for. You just make sure to subtract out the volume of the actual gas particles. But the attraction and repulsion thing is a little bit more complicated. So these deviations that you see, it really depends on how frequently the particles collide and how close the particles can get to each other when they're not colliding. Depending on how close or far away the particles are from each other, the attractive effects might dominate or the repulsive effects might dominate, and that's why you see, for example, at low pressures, the compressibility seems to go down a bit, and then once the pressure starts going up past a certain threshold, it only ever continues going up. High pressures are usually associated with low volumes. Think of Boyle's law. So high pressures, high frequency of collisions, a lot of time spent with the particles getting really, really close to each other. When the particles are really, really close to each other, repulsive effects tend to dominate, which forces the particles to kind of spread out more than you would predict them to according to the ideal gas equation. So that kind of explains why compressibility goes up under high pressures. But yeah, so the other thing, just in general, don't worry about compressibility going up or down. You probably don't need to know that even if you're a college student. But the thing to remember is those collisions are not perfect. So the more of them you have, the more messed up your graph is going to become. The more deviation you're going to have from ideal behavior. So what's the solution? One, have fewer of these screwy collisions. How do you do that? Lower pressure. Like I mentioned earlier, low pressure helps gases behave closer to ideally. At low pressures, there are going to be fewer collisions, and the fewer of those messy collisions, the better. But also high temperatures. If the temperatures are really, really, really high, then the particles are going to be moving so fast that there will be less time for the attractive and repulsive effects to, influence anything. So high temperature makes it so that even if you do have a collision, the collision is going to be closer to perfect collision. So that's the basic idea behind ideal versus real gases. Real gases don't behave like ideal gases at all. That's why the ideal gas equation needs to be modified. And one of the modifications that's presented to the ideal gas equation is something known as the van der Waals equation, which is right here. So the van der Waals equation takes the ideal gas equation and modifies it slightly. There are more accurate gas laws that are even better than the van der Waals equation, but even the van der Waals equation is one that's a little too messy. You don't really need to know it. I highly doubt that you do, but just in case, I'm going to give you a quick example because it is pretty easy to use. You just need the right data tables available. So, as you can see on the screen, they add this factor that supposedly corrects for molecular attractions, and there's also another term over there that they subtract out of the volume. That part makes sense. You're basically subtracting out the size of the molecules from the size of the container so that you can, get the correct volume of available space for the particles to freely move around in. And yeah, so that's the van der Waals equation. Let me show you this chart that has all of the van der Waals constants for a couple of gases. So there's a couple right there. So there's the A values and the B values that you plug in. And otherwise, it's really just straightforward. You just plug in numbers into the equation and you grab your calculator and you're pretty much done. So to wrap things up, let's do one van der Waals problem and then we'll call it a day. So we've got a 4.25 liter flask, contains 3.46 moles of carbon dioxide at 229 Celsius. Calculate the pressure of this sample of carbon dioxide from the ideal gas law and from the van der Waals equation, and explain the reasons for the differences. I think we'll skip part C because we've already talked about it. Let me take a sip of water real quick. Okay. Now let's go ahead and get cracking at this. I think my throat is trying to tell me that I've been talking for too long. Okay, so 4.25 liters, that's your volume. Moles, we've got 3.46. Temperature 229 Celsius. In kelvins, that will be 502 kelvins. Okay, and we know the identity of the gas is CO2, and we need to calculate the pressure. So it's CO2, and we need to find pressure. Okay, so first, using the ideal gas equation should be pretty easy. Pressure equals nRT over V. So we've got pressure equals 3.46 times 0.08206 times 502 over a volume of 4.25. And that should give us the pressure in atmospheres. So let's see, 3.46 times 0.08206 is 0.284. 0.284 times 502 is 143. 143 over 4.25 is 33.6. So I'll call it P ideal equals 33.6 atmospheres. And then for P real, let's look back on our van der Waals equation. Let's see, I'm going to hide that, and so we've got P plus AN squared. So P plus an squared over v squared times v minus nb equals nRT. This requires more algebra. Let's go ahead and figure out what the A and B values are for CO2. So there they are on the screen. A is 3.59, B is 0.0427. I'm going to write those down. A equals 3.59 and B equals 0.0, was it 4? Yeah, 427. Okay. And I've got those written down. Now I can switch back to my doc cam. And let's see. So I might need another sheet of paper for this. So we've got P plus 3.59 times 3.46 squared over v squared, so that's 4.25 squared. And then all of that times 4.25 minus NB, so 3.46 times 0.0427 equals nRT, which I calculated earlier, so I'm not going to recalculate it again. We had 143, right, for the numerator of this. This was 143. So that's what I'm going to write down there. Save myself a bit of time. Okay, so first I'm going to calculate this part. So 3.46 times 0.0427 is 0.148. And then 0.148, so 4.25 minus 0.148. If I round to 2 decimals, that's 4.10. So this part right here gives us 4.10. Can you see that on the screen, or is it too low? There it is. And then I'm going to go ahead and divide this over. So 143 over 4.10 is 34.9. I guess I'll continue up here. I really don't want to have to bring out a fresh new sheet just for one line of algebra. So P plus, I'll calculate this stuff in a minute, is equal to 143 over 4.10, which was 34.9. So let's see, what's this stuff going to be? So 3.46 squared over 4.25 squared, I'm going to do 3.46 over 4.25, and then I'm going to square that. So 0.814 is the result of 3.46 over 4.25. If I square that, I get 0.663, and then 0.663 times 3.59 is about 2.38. 2.38. Subtract 2.38 on both sides, and the real pressure, at least according to van der Waals, is 34.9 minus 2.38, rounding to 1 decimal, would be 32.5 atmospheres. Okay, so it looks like the ideal gas equation wasn't too far off this time. 33.6 and 32.5, those are pretty close to each other. So yeah, the real pressure is lower than the ideal pressure. I guess... what would the reasoning be? I mean, well, it's molecular attractions and volume, obviously, but specifically for this one, what would it be? So, of course, the volume is an overestimate, so when you overestimate the volume... Wait, but if you overestimate the volume, that would lower the pressure. So it looks like molecular interactions were a bigger factor here. Yeah, molecular interactions must have been a bigger factor in this one. So that's just following the math. Again, you don't really need to care too much about this. Maybe I'm just nitpicking too much, but you know, for the people who do care, I don't mind briefly talking about it. So yeah, there we go. There's the ideal pressure, there's the real pressure, and there's the one and only van der Waals example in that book that I could find. Just goes to show you how unimportant it is at this point. The van der Waals equation and other equations for real gases become more important when you start taking some of the more advanced chemistry courses. But yeah, I think that'll be it for this video. Hopefully you learned a lot. Something tells me that this video is going to be the longest one ever. But yeah, hopefully you enjoyed it despite its length, and hopefully it was informative and helpful and covered every little thing you needed to know on top of all the little things you probably didn't need to know. The plan for next time is to cover thermochemistry. Judging by my note card, that one might go by quicker, but I'm not going to make any promises. When I make promises, the powers that be seem to modify the world in such a way that I can't keep them. Plus, I enjoy talking at length about all these different topics. I mean, sure, it's probably a drag, but at least I get all that information out there and I don't have to redo different topics or worry about which topics I included and which topics I overlooked. Just knowing that you covered everything really helps you keep track of what you covered. So I'm probably going to keep at this, looks like 5-hour average video length. But yeah, next time is thermochemistry. Prepare yourselves. There's more calculations to do. Once we are done with thermochemistry and then electronic structure, we'll start to move into territory that's less calculator heavy. So those of you who hate using your calculators, rest assured you're going to get some time to breathe very soon, but not in the next video, about halfway into the video after the next. This has been Al the Tutor, reminding you that ignorance is not bliss. Take care, and I'll see you next time.